I'm going to tell you about what the FAA has been doing for the last 2 years and something we're calling the Transport Airport or Aircraft Performance Planning Group. A little bit about myself. My name is Kobe Johnson. I work for the FAA in Washington headquarters in flight standards. My background was Air Force. Then I worked for the FAA back in the 70s when you couldn't get an airline job. And then I got an airline job in the 80s for almost 20 years. Piedmont/U.S. Airways, and then I quit the airlines when you didn't want an airline job and went back to the FAA, and that's where I've been for several years now. But I want to tell you a little bit about this group, and I'll introduce these folks in a second. But first of all, why are we even doing this, and what is it all about? Somebody's already asked me, well, what is this all about? In the early 1990s, AFS 400, that's my division in the FAA, became responsible for an AC called 120-91, which is Takeoff Obstacle Analysis. It's really and truly the only FAA document that's operationally oriented to the operator out there on how you conduct takeoff obstacle analysis. And there's a couple esteemed members of our group here who are actually the original authors of that I'm going to introduce you to lately. But really over the past 15 years, there's been this huge proliferation of business jets in the aviation community, over 11,000. And you know, I remember when my first stint with the FAA, when a Part 135 operator flew Navajos, and those days are gone. And a lot of folks are flying jet aircraft, very modern, high equipped aircraft, and Part 135, and of course 91 and 91K operations. So, and of course more than half of those are flown by U.S. operators with N numbers on them. But we've had some reports over the past several years that we need to clarify from the FAA standpoint not only the aircraft certification requirements for Part 25 airplanes that are understandable by flight crews, not just engineers, but something that they use in their everyday operations. But also we have a huge need to educate our FAA POIs out there on their responsibilities when it comes to overseeing their operators out there. And I know there's lots of stories. I've heard them all. So anyway, as far as the TAP goes, it cranked up around just about 2 years ago. And we came up with a charter, and it was to improve the operator and inspector knowledge of CFR Part 25 aircraft performance. Now, there's a difference between TERPs and aircraft performance, and I think everybody basically understands that. But TERPs is something that the basic pilot just doesn't have to care about because he has an instrument approach plate or procedure, departure, star, or something like that, that is already done for him. And all he has to do is be trained and understand how to fly that procedure, and he's A-OK. There's another side to the whole jet flying business, and that's the understanding of aircraft certification requirements, particularly when it comes to things like one engine and operative takeoff planning. That's something that everybody has to be responsible for, and there has been very little work done, particularly by the FAA and the industry, in making sure that that knowledge has been put forth. So we put together this group, members of FAA Flight Standards, Aircraft Certification Office, that's an FAA certification function. SAPO is a Society of Aviation and Professional Operational Engineers. NBAA, ALPA, and other industry subject matter experts to sit down and identify, what we needed to do. So first of all, we had to identify the audience. And it's you folks. It's the 91K operators, Part 135 pilots that fly these magnificent airplanes. It's not the Part 121 airline pilot. They're already spoiled. I know, I've been there. We sat there at the end of the runway waiting for a dispatch department or a department of very knowledgeable operations engineers to send us the numbers, and we'd get it on ACARS, plug it in our flight management computer, and blast off. And we were assured of all the certification requirements were being met. You, unfortunately, could be in a situation, and I know you've all experienced that, where you could be on the other side of the world with a Part 91 operation and literally be on your own. And unless you have procured the services of some of the vendors out there that offer aircraft performance planning, you are literally on your own. And I think at the end of this this presentation, you'll see what we're saying there. But we're also concerned about the Part 142 performance training activities out there. If you arrive at your recurrent training course and the instructor stands up and gives you a performance problem for your airplane and a bunch of spaghetti charts, I call them, that I've never been able to figure out. I've got 7 type ratings, and I've always had that issue on the oral. Well, the guy says, well, that's pretty close, but you just didn't get it. And I insisted that this group put together something that was operationally friendly and pilot friendly. So you're not going to see any spaghetti charts, except you'll see some sliding in some of the video in the background. But we're gonna focus on what the pilot and flight crew needs to know operationally. So that's the audience. And of course, like I said, our FAA inspectors and our formal training representatives that oversee the Part 142 school issue. So the TAP, when it got together, established some goals. One thing we wanted to do is we wanted to be committed to addressing these misunderstandings and clarify aircraft performance planning for pilots. We wanted to find, or the end game is to actually come up with sort of a level playing field out there for all the Part 91 and 135 operators. Level playing field, what do I mean by that? Well, I know of a POI in California at a FSDO that authorizes his operator to fly full on every takeoff without having regard to aircraft performance calculations, because he doesn't understand his responsibility. I know of an adjacent FSDO POI who does understand this stuff, makes his operator toe the line, same airplane, so he's got to pull weight off. So you have here you have a competitive disadvantage by doing things right, and we need to correct that. And so that's one of my personal goals anyway. But the other thing is to improve the knowledge and performance and best practices industry-wide, and to differentiate, like I said, between Part 25 certification standards and TERPS criteria. This presentation basically has 4 modules. Understanding something called declared distances. You may know about this, you may wonder about it, you may have heard about it. We're going to go into great depth. Unfortunately, for some, you will think initially, but at the end of the module, I think you will see where we're trying to get to. Declared distances is something that's fairly new in the aviation safety business, but it's here and it's alive and it's well, and we were living with it. What runway takeoff performance, landing distance assessments, and departure planning. Before I forget, in front of you we've got notes that follow the modules so you can keep track of them, and we're going to stop periodically throughout the presentation. It's going to be a pretty long day, so we're going to take breaks and so forth. And we've got our experts here, so you'll be able to ask questions after each specific module. So just as an example of OEI, one engine and operative planning, this is a departure for the WAGI 2 for Reno, 16 right and left. It has all engines departure of a 940 feet per nautical mile, which is a screaming climb. And you see, you come down here about 13 miles to this intersection, hang a left and head on that way to get out of the mountainous terrain down here. If you lose an engine, the procedure should be in the cockpit, and you brief the WAGI 2, and then you say, if we lose an engine, for Part 91 operators, you have something called a textual procedure, special departure procedure. And this basically says, if we lose an engine on this departure, we're not going to go all the way to 13 miles, we're only going to 3 miles, hang a left, and we're going up to Mustang VOR and hold a climb in the holding pattern until we get, clear the terrain. So this is what the Part 91 pilots have traditionally had to put up with and are still putting up with today, is this textual. So you've got to visualize in your mind what these words mean. What we had in the 121 airline world was this, and this is also for Reno. This is a special departure, and in this particular case, This basically has the ILS, and if you miss, there are waypoints that are already put in your flight management computer. I've flown this in a simulator, 1 engine out or 2 engines operating. This happens to be the same procedure for the normal missed approach on the ILS and for the engine out ILS. But basically, it's a tight left turn here that gets you up over Lake Tahoe. And the reason we built this is this ILS initially had minimums of 800 feet, really high for Reno. And by able to have this missed approach procedure, which kept you tucked inside the high terrain, we were able to get the minimums down to 200 foot. So, I mean, that's the greatest of both worlds. If you lose an engine, you fly the same procedure as you would normally. You don't have to do something differently. Now, the airlines, I mean, when I was flying, this is a Jeppesen plate, and I thought this was an FAA-approved procedure. I mean, it looks like one. It's not. These engine-out procedures are accepted by the FAA, and they're developed by each individual air carrier. Their operations engineering department, they have a very lengthy process they go through at many of the airports. They fly all over the world where they provide this information to the crews. But you see, my wish would be that the Part 91 guys and 135 guys have this sort of depiction to be able to follow, because it just makes sense to me. And we have actually a video of this, right? It's a animation. It happens to be at Low Airlines. Unfortunately, they're out of business now, but they were the first ones that came up with that, little Low Airlines. And we actually have an airplane animation flying over a sectional. Kind of neat because you can see the elevations and so forth. And I don't know if we can get it going or not. Okay, you see we're coming down, and these are actually the runways up here. Here's the airplane, and you'll see something pop up here in the corner if you just pause that, Chris. Got to go back. We'll try it again. The reason I wanted to show you this is the the God's view of the airplane. Here's the approach coming down. Oh, it happened again. Okay. Well, we'll just leave it run. And what happens is as he gets close to the missed approach point, you'll see the airplane pull up, and here is the depiction of the airplane coming in here, and here's the runway. You can see the runway complex right up in here. And see all that high terrain down here. So what this missed approach procedure does is it lets them basically stay inside this relatively lower area here with a fairly tight turn. Being an FMC, what we call a track analysis method in 120 Part 91, it precisely follows this track and kills the winds if you're flying it on autopilot or manually or not. You just fly the procedure as depicted. So it's really takes a lot of weight off the pilot's shoulders when they're trying to get through this kind of thing. And here he's making a turn, and this sectional I like just because you see the elevations out there. And it basically keeps him in the valley, back out over the airport, and he goes out over here, and Lake Tahoe is up here somewhere. Now, that one textual description I showed you before had the airplane climbing way out over in this area here toward the Mustang VOR, which is actually up here. So this is the, just the preferred way of doing stuff. So this is the kind of area we'd like to move into FAA-wise for everybody who's flying these high-performance airplanes to have available to them to be able to do one engine out extractions. Go ahead, Peter. I'd like to acknowledge these folks here. We worked very hard on this video that there's a set of videos you're going to see. Bombardier, Jeppesen, APG, and ASAP. We've got an ASAP fella here with us today. Jeppesen, we've got Diane Swanson here. Boeing, we're going to introduce Rob Root. And Delta, we have Roy Maxwell here, also president of SAPO. And NBAA, which has been a huge supporter of us in the development of this program. I want to emphasize that when we get done with this thing, and we're almost done, our whole purpose was to develop a performance training program that we can give to you guys. We're going to have it available on probably the NBAA website, maybe the FAA website. I hesitate to do that because no one could ever find an FAA website, including me, without Googling it. and it's just kind of a stupid way to go. But NBAA is a great website, and we're also going to have DVDs available for Part 91 and for you training folks to do that. You'll see as we go through each of these modules, there's a lot of information, water out of a fire hose kind of thing, but if you have a good ground school instructor, you can see if you exercise a pause button and say, okay, let's look at this chart, or let's look at this diagram, or let's look at this concept. You can see where this thing could really bring in a flood of good information to your crews. These guys from FlexJet actually participated in a simulator exercise we're going to show you, an engine out scenario coming out of Aspen, Colorado. And Dick Wolf was tremendous in procuring that simulator for us in Dallas at the Bombardier Aircraft Training Center. And I'd like now to introduce to you the panel members. To my right here is Don Stimson. Don got his degree in aerospace engineering from the University of Virginia. He began his career at Boeing in 1980. He moved to the FAA in 1991. He's been there ever since, and currently is the daddy rabbit of the FAA's Aircraft Certification Performance program. He's participated in the development of 120-91, the only FAA advisory circular that addresses these issues, and we're just really, really happy to have Don on our side. Rob Root is second. He graduated in 1987 from Embry-Riddle. With a Bachelor of Science in Aeronautical Engineering. Rob's a pilot. He worked briefly at Honeywell, Commercial Flight Systems. He joined the aerodynamics engineering staff at Boeing Commercial Airplanes in 1989 and has spent the better half of his next 7 years defining FMC performance functions and data for the 73 and 757 models. Rob has been a great asset to the TAP. And he moved to actually the Boeing Flight Operations Engineering in 1996, and he was responsible for a lot of the high-speed performance activity on the 757, 767. Rich Bowl, third over, is our NBAA rep. He's type rated in 5 biz jets, over 9,000 hours total time. He has 3 years as a Part 142 training instructor. Rich has been hugely important to this whole effort, put a ton of his own personal time in. He's vice chair of the NBAA's Access Committee, chair of the Advanced Flight Deck Technologies Working Group, and co-chair of the TAP Working Group. Roy Maxwell on the end there is a senior principal engineer for aircraft performance for Delta Airlines. He owns all those ops engineers at Delta Airlines on 14 or 15 or 16 different types of airplanes. I can never keep up. You can't either. He wrote some of the first airport analysis computer programs in the industry in the late 60s. Roy is the preeminent person in the airline industry when it comes to this aircraft performance and how to get it to the flight crew so they can understand it. He chaired the ATA FAA group that actually drafted AC 12091 with Don, and we're really glad to have Roy with us. Chris Jones behind me here, he's running the computer. He's retired from Air Force after 23 years in active duty. He worked in the 89th in the Presidential Flying Group over there at Andrews Air Force. He flew Air Force 2, and he held positions as Chief Pilot, Chief of Standards, Training and Ops Officer. And he's also an aero engineer, and he's worked very hard with this group in developing this program. Down in the front here, we have Diana Swanson from Jepson. She has a Bachelor of Science from Michigan State, or Metropolitan State University of Denver, and a Master's from the University of Denver in Applied Communications. She has been at Jepson over 22 years, the last 11, primarily in the role of Information Safety and Auditing for the Office of Aviation Safety. She took a critical interest in cleaning up the portrayal of runway information and data on the Jepson airport charts, and has been a very, very important member of our team. And then Gary Craig is with ASAP. That's one of the vendors I spoke to earlier that you'll see their logos in here. Did some great work for us as an airport analyst and quality assurance specialist. He holds an ATP, came from PSA Airlines, and it shows I have a captain over 15 years and accumulated over 14,000 hours. So that's our group of experts up here. And all I'm going to say is OEI planning pays off. So that's a real picture of a real airplane with a whole bunch of birds. Okay. So this fellow here, we're going to go into something called declared distances. And I don't know if you've seen this or not. It's pretty amazing. This fellow here didn't do his takeoff performance planning exactly as I think you would like your guys to see it done. So I think we actually have a little audio with it. Doesn't look good. Looks bad. Looking real bad. Don't you love it? Yeah, I'd like to talk to him. Anyway, that's what we're going to talk about now. We have our first section on declared distances. Now, I'll warn you, declared distances, you're going to see a whole bunch of stuff coming. We're going to stop it and explain stuff and clarify stuff as we go along. But at the end of the day, particularly in the latter part, I think you'll find that stuff that you thought in your flight management computer was gospel is maybe not.
Declared distances. Learning how to use and interpret declared distances data. The runway required for takeoff and landing of a jet transport airplane is an important calculation that every pilot must complete before or during a flight. An important element in this calculation is the knowledge of the usable length of runway available for the takeoff and for the landing operation. Therefore, it is important that pilots be aware of the concept of declared distances as a means of reporting usable runway lengths for takeoff and landing. Here we see a flight crew briefing the runway available for takeoff at the McCollum-Cobb County Airport near Atlanta. The runway at McCollum is 6,311 feet in length. However, the crew refers to the FAA Airport Facility Directory to see if declared distances have been published for this runway. Looking at the declared distances for runway 27, the crew notices that the takeoff run and the takeoff distance available are both 6,311 feet. However, the accelerate stop distance available is only 5,374 feet, a difference of over 937 feet. The pilot appropriately alerts his first officer to this fact to ensure no computation errors are made. Awareness of declared distances is key to ensuring accurate arrival and departure calculations. Declared distances refer to the length of runway declared usable for takeoff and landing for the purpose of airplane performance calculations. The accelerate stop distance available is the runway plus stopway length declared available and suitable for the acceleration and deceleration of an airplane aborting a takeoff. The accelerate stop distance available may be longer than the physical length of the runway when a stopway has been designated available by the airport operator, or it may be shorter than the physical length of the runway if the runway lacks an adequate runway safety area or in some other way does not meet runway design standards. Takeoff run available is the runway length declared available and suitable for the ground run of an airplane taking off. Takeoff run available is typically the physical length of the runway, but it may be shorter than the runway length if necessary to satisfy runway design standards. For example, the takeoff run available may be shorter than the runway length if a portion of the runway must be used to satisfy runway protection zone requirements. Takeoff distance available is the takeoff run available plus the length of any remaining runway or clearway beyond the far end of the takeoff run available. The takeoff distance available is the distance declared available for satisfying takeoff distance requirements for airplanes where the certification and operating rules and available performance data allow for the consideration of a clearway in takeoff performance computations. Landing distance available is the runway length declared available and suitable for a landing airplane. The landing distance available may be less than the physical length of the runway, or the length of the runway remaining beyond a displaced threshold if necessary to satisfy runway design standards. In most cases, a runway's declared distances equal the physical length of the runway, or in the case of the landing distance available, the length of a runway remaining beyond the displaced threshold. However, this is not always true with every runway. Runway design standards ensure adequate protection from obstacles, other airplanes, vehicle traffic, and undesirable activities surrounding the runway and in the immediate vicinity of the takeoff and landing path. In most cases, the environment surrounding the runway permits the full use of the runway for performance planning purposes. However, there are some runways that are geographically constrained, and a portion of the runway's usable length must be used to meet these design standards. For example, a runway safety area may extend into the usable portion of the runway, limiting the length of the runway that may be used for performance planning related to stopping the airplane, such as accelerate stop distance available and landing distance available. Let's look at how declared distances are used with takeoff and landing runway requirements for turbine-powered transport category airplanes. The accelerate stop distance is the distance required to accelerate to a point in the takeoff, then in response to an event take the first action to reject the takeoff at a speed no greater than v1 and to bring the airplane safely to a stop. Originally, the accelerate stop distance did not include consideration for events other than engine failure that could lead to a rejected takeoff. In 1978, the certification rules were amended to consider both engine failure and non-engine failure scenarios. Accelerate stop distance is now the longer of the distance with one engine failing just prior to V1, or with all engines operating throughout the rejected takeoff. In response to the disproportionate number of rejected takeoff accidents on wet runways, the certification rules were again amended in 1998. Manufacturers are now required to provide wet runway accelerate stop distance and wet runway takeoff distance data in the airplane flight manual for all newly type certificated transport airplanes, and the operating limitations for these airplanes require the use of this data when the runway is wet. The accelerate stop distance required for takeoff will be the longer of the dry runway accelerate stop distance or the wet runway accelerate stop distance. The calculated accelerate stop distance cannot be longer than the accelerate stop distance available. The takeoff distance is the distance from the start of the takeoff roll to the point at which the airplane attains a specified height above the takeoff surface. For a takeoff on a dry runway, the takeoff distance is the longer of the one engine inoperative takeoff distance to 35 feet above the takeoff surface, or 115% of the all engines operating takeoff distance to 35 feet above the takeoff surface. For airplane types certificated after 1998, when taking off from a wet runway, the takeoff distance will be the longer of the one engine inoperative takeoff distance to a height of 35 feet above the takeoff surface, if the runway is dry, or the one engine inoperative takeoff distance to a height of 15 feet above the takeoff surface, if the runway is wet. On a wet runway, the all engines operating takeoff distance is 115% of the distance to a height of 35 feet above the takeoff surface. The longer of the one engine inoperative takeoff distances for either a dry or wet runway, or 115% of the all engines operating takeoff distance to 35 feet, establishes the minimum takeoff distance when a runway is wet. The calculated takeoff distance cannot be longer than the takeoff distance available. The takeoff run distance is a consideration when the takeoff run available is less than the takeoff distance available. For example, when the runway has a designated clearway usable for takeoff planning, the takeoff distance available will be longer than the takeoff run available. The takeoff run is the longer of the distance required from the start of the takeoff to the midpoint between liftoff and the point at which the airplane attains a height of 35 feet above the takeoff surface, with one engine inoperative, or 115% of the distance required from the start of the takeoff to the midpoint between liftoff and the point at which the airplane attains a height of 35 feet above the takeoff surface, with all engines operating, whichever is longer. The takeoff run applies only on a dry runway. The calculated takeoff run cannot be longer than the takeoff run available. When taking off from a runway where the takeoff run available is equal to the takeoff distance available, the airplane's takeoff run may be considered to be equal to the airplane's takeoff distance. The landing distance demonstrated during certification is the distance required to come to a full stop from a point where the airplane is 50 feet above the runway. Air carrier, on-demand, and fractional operators must plan their flight such that their landing weight at the destination airport and the alternate airport, if one is required, will permit the landing distance demonstrated during certification to remain within 60% of the landing distance available. These operating rules impose a limitation on takeoff weight in consideration of the fuel used in flight. For eligible on-demand and fractional operators that meet certain qualifications, including the use of an approved destination airport analysis, this requirement is adjusted such that the landing distance demonstrated during certification must remain within 80% of the landing distance available. FAA guidance recommends that as close as practical to the time of arrival, flight crews perform an assessment of the actual landing distance required based on the reported weather and runway conditions and include an additional 15% safety margin. The minimum runway required resulting from this assessment must be less than the landing distance available. The airplane operating rules and/or airplane operating limitations establish minimum distance requirements as well as weight limitations for takeoff and landing and are based on performance data supplied in the airplane flight manual. The minimum distances required for takeoff and landing, obtained either in planning prior to takeoff or in performance assessments conducted at the time of landing, must fall within the applicable declared distances before the pilot can accept that runway for takeoff or landing. Declared distances are published in the FAA Airport Facility Directory for runways where they have been established. In the not-too-distant future, all Part 139 certificated airports, which are those airports with scheduled air carrier operations, will have declared distances published. In some instances, an airport may shorten declared distances for a runway when it is necessary to meet runway design standards. This is the case with Cobb County McCollum Airport near Atlanta, Georgia. However, there are many runways that do not have declared distances published. For runways without published declared distances, these distances may be assumed to be equal to the physical length of the runway. If the runway has a displaced threshold, then the landing distance available is assumed to be the runway length less the amount of the threshold displacement. Pilots who use U.S. government instrument approach charts and airport diagrams may recognize the inverse D graphic symbol. This symbol is also used to inform operators that there are declared distances established for one or more runways for this airport. The pilot should consult the FAA Airport Facility Directory to obtain these distances. Temporary partial runway closures, such as this example from Lubbock, Texas, may include a notice to airmen reporting revised distances. Pilots must be aware that the runway lengths stored in the navigation database of the GPS or flight management system may not reflect the runway's declared distance. The runway length at McCollum-Cobb County is 6,311 feet, which is the same value stored in the navigation database. Flight management systems for many business aircraft incorporate performance calculation functions. These functions can compute the takeoff and landing distances required for conditions and have the capability of calculating the maximum allowable takeoff or landing weight for a particular runway. However, these calculations are based on the runway information stored in the database. The runway length stored in the navigation database may not reflect a runway's declared distances, or the length of a runway remaining beyond a displaced threshold available for landing. For those flight management systems that do provide takeoff and landing performance calculations, the results of these calculations may not reflect the true maximum allowable takeoff and landing weight for that runway based on conditions. For example, the flight management system for this airplane calculates a maximum allowable takeoff weight of 38,247 pounds for takeoff on runway 27 if the runway is wet. However, the runway analysis for runway 27 reports a maximum allowable takeoff weight of 35,656 pounds, a difference of over 2,500 pounds. If the crew relies on the flight management system to compute their required takeoff field length, which in this example is 6,273 feet, they may not be warned that this value has exceeded one of the runway's declared distances. The 6,273-foot takeoff field length required exceeds the runway's accelerate stop distance available of 5,374 feet. The flight management system will provide no warning message of this exceedance. As you can see from this view, the Cobb County McCollum Airport's runway 27 has a physical length of 6,311 feet. However, both the declared accelerate stop distance and the landing distance available are 5,374 feet. This is 937 feet shorter than the physical runway length. There is no displaced threshold on runway 27, so some pilots may wonder why these distances are reduced. The last 937 feet of runway 27 is used to satisfy the requirement for a 1,000-foot runway safety area. The application of declared distances is intended to ensure that with respect to airplane performance capabilities only, the airplane has the capability of stopping during the landing maneuver or in the event of a rejected takeoff before intruding into the runway safety area. For this reason, the declared accelerate stop distance available and the landing distance available is less than the physical length of the runway. The takeoff data furnished for most business jets provides a minimum takeoff field length required based on takeoff weight, takeoff configuration, and environmental conditions. When the manufacturer provides takeoff performance data that shows only one minimum runway length, this length must not exceed the most restrictive of the takeoff declared distances of accelerate stop distance available, takeoff run available, or takeoff distance available. The minimum field length required for takeoff is usually based on the balanced field concept, which is a condition where the selected takeoff V1 speed results in accelerate stop distance being equal to the one engine inoperative takeoff distance. A small number of business jets are furnished with unbalanced field takeoff data that allows for the independent calculation of takeoff distance, takeoff run, and accelerate stop distance. These airplanes can realize a takeoff weight advantage over an airplane that is limited to balanced field takeoff data by calculating an unbalanced V1 that may be higher or lower than the balanced value, depending on the declared distances available. If the runway remaining beyond the end of the accelerate stop distance available is included in the takeoff run available and the takeoff distance available, then by using the unbalanced V1, this remaining runway may be used for calculating the takeoff run and takeoff distances to permit an increase in maximum allowable takeoff weight. However, the use of unbalanced takeoff data is an involved process. Use of an airplane performance planning software tool or an airport engineering service that furnishes a runway analysis is recommended. A number of business airplane operators use airport diagrams and instrument approach procedure charts furnished by a commercial provider, for example Jeppesen. On their charts, Jeppesen publishes usable runway lengths, not declared distances. The usable length concept was created many years prior to the formal creation of the declared distance concept and continues to be published on their charts in lieu of declared distances. Usable length takeoff is almost identical to takeoff run available, and usable length landing beyond threshold is similar to landing distance available, but they are not takeoff run available and landing distance available, and Jeppesen does not incorporate anything similar to accelerate stop distance available and takeoff distance available on these charts. When a takeoff value and/or landing value is available from source information that is shorter than the runway, Jeppesen wants to display the more conservative values. Jeppesen also publishes notes or otherwise explains length deficiencies or unique usable lengths. When the landing length is shorter than the full runway length, and this is not due to a displacement, then an additional explanatory ball note is applied, reading similar to the following: last 900 feet is unavailable for landing distance computations. A displacement is accounted for on the charts, not in a length value, but rather in a displaced threshold symbol designation on the charted runway. Jeppesen's charts are meant to be used for flight and navigation in the first place and flight planning in the second place. Jeppesen additionally offers other products and services specifically for flight planning. The full runway length will always be applied on the plan view to serve pilots' overall needs, as well as unplanned emergency decision-making. It is important to understand that the application of declared distances has no bearing on the operational use of the runway for taxi, takeoff, and landing rollout operations, provided the runway surface is appropriately marked as usable runway.
Now you're going to see some more terms that are going to come up there, TOR and RSA and everything. The bottom line is, in this declared distance business, there's 4 things that you need to know. Takeoff run available, TORA, TOTA, takeoff distance available, which includes the length of the clearway provided. Accelerate stop distance available, ASDA, and landing distance available. Those are the 4 key things to declare distances. But what's it all really mean? By 2015, all the Part 139 and the airports have to have these declared distances defined. So what it means, if you think you have a 6,311-foot runway and they cannot provide a 1,000-foot safety area off the end of that runway, they're going to take what? They're going to eat the runway to get that 1,000 foot. It may be this much, maybe 600 foot. So you actually lose, for your accelerate stop distance available, that effective runway length that you thought you have, and it's going to be in your nav computer or your flight data computer as 6311, when actually it may be 5,300. So I mean that's an important point here, I think, to get across. But the main thing is, as far as declared distances go, they are applying to resolving this runway safety area. It's 500 feet from here to here, and 1,000 feet on either end. And then if you can't provide that safety area, then you have to eat the runway up accordingly with these terms. So,
for example, landing distance available for runway 9 must be used when showing compliance with the landing distance requirements specified in the operating rules or listed in the airplane's operating limitations, or when making a before landing performance assessment. The landing distance available is less than the physical runway length, not only because of the displaced threshold, but also because of the subtractions necessary to meet the runway safety area beyond the far end of the runway. However, during the actual landing operation, it is permissible for the airplane to roll beyond the unmarked end of the landing distance available. Likewise, the accelerate stop distance available for runway 9 must be used when showing compliance with the accelerate stop distance requirements of the airplane operating rules and/or airplane's operating limitations. The accelerate stop distance available is less than the physical length of the runway due to subtractions necessary to achieve the full runway safety area requirement. However, in the event of an aborted takeoff, it is permissible for the airplane to roll beyond the unmarked end of the accelerate stop distance available, as it is brought to a full stop on the remaining usable runway. In summary, it is perfectly acceptable to operate on any portion of a runway that is appropriately marked as usable runway, regardless of a runway's declared distances. These declared distances are for calculation of performance limits only.
Again, a lot of information, but again, if you have a good ground school instructor, you could go through this thing a lot slower and slow it down. But I think some points probably were pretty evident. They were to me that, number one, you can't rely on your flight management computer to give you the information you need to meet these requirements. Actually, the only place you can get it is in the FAA Airport Field Directory, which you can get online, by the way, now. That little D they had on the NOAA charts, the reason that is there is because they didn't want to clutter up the chart with all these declared distance numbers, so they say, go here and look. Jepson in their Volume 1 does provide some of the declared distances, but they've decided not to do that. And there's a couple reasons about that. One is they don't want to clutter up the charts. And second, I think, is that the whole concept has been evolving in the FAA and in the aviation community to best understand how to get this very important information to the flight crews, and in what fashion would be the best possible way to do that. But this is something called the balanced field takeoff length, and I'm going to ask Roy Maxwell if he wouldn't just kind of give the basic concept behind this that he explained to us earlier.
But declared distances used to be pretty simple before the FAA got involved with it.
Yeah.
The
Industry,
Tor-
FAA.
the,
Industry.
the Torah, and it wasn't him, it was the airports division, all right?
Yeah.
But the Torah was the length of the runway. And I used to have trouble remembering the declared distances, Torah, TOTA, ASDA, LDA. Well, LDA's landing, okay. ASDA, accelerate, stop, I can remember that. But it never made sense to me, this takeoff distance, takeoff run business, until I figured out that the one with the R in it, the Torah, is the runway length. And then the TOTA is the runway length plus the clearway. And then the accelerate stop distance is the runway length plus the stopway. Those are the traditional distances before the airports division got involved in shortening these declared distances because there wasn't an RSA.
Right.
So the two basic ones that we have then are the either the Torah or the TOTA if you have a clearway for the accelerate go case, and then the ASDA for the accelerate stop case. And this balanced field length, it says that we're going to make them equal. Well, if they are equal, that's fine, because and typically that's what you have on a runway.
Yeah.
But if you have, if you're, and so that's how you select your balanced field length V1. One of the more confusing things is, and I've heard pilots thinking in terms of a balanced field length takeoff, is one in which they don't have any excess runway. In other words, your actual takeoff weight equals your limit takeoff weight. Well, that's not what balanced field length is all about. It's what happens when you are not takeoff weight limited, that you have your choice of adjusting your V1 up or down a little bit. You can see that, of course, as V1 goes up, it's going to take longer to stop. So that's what the accelerate stop line is all about. And as V1 goes down, it's going to take longer to accelerate with an engine failure and continue the takeoff. So the minimum point at which the minimum runway required is this balance where they're equal. And in the old world, that's what everybody did. If you don't know whether you're using balanced V1s or not, you are. Because the alternative is the customized V1s that are customized for every runway. And the point that you need to take away from this is that if you're using balanced V1s, then you have to use the field length associated with the smallest of the Torah, TOTA, and ASDA.
Thanks, Roy. Okay, so this whole discussion on declared distances is basically trying to prevent this. Now, you remember Challenger, Teterboro, Runway 6, this building, after he went through the fence and across Route 46, went into the clothing factory, I think it was, that building was 526 feet from the end of Runway 6. You're supposed to have 1,000 foot. So you can see where the runway safety area concept came from. You probably remember, I think it was about 8 years ago, a CL, a regional jet, CL 200, I think it was, taken off on runway 23 at Charlie West, Charleston, West Virginia. Aborted the takeoff. If you're familiar with Charleston West, you know that's not the way to be aborting the takeoff because there's a cliff at the end of the runway. They had EMAS installed. EMAS will take that 1,000 feet. I think it'll take it down to a 600 foot or something will be an acceptable reduction. That EMAS literally saved 34 passengers from dying, from going down, plunging down over the end. It's great stuff. Real expensive. One block of EMAS is around $1,000, and they average between $4 and $8 million per installation, depending. But I know of 8 or 9 EMAS incidents in the last just couple of years. Everything from a light twin in Key West to a 747 at Kennedy that have resulted in no injuries to passengers, crew, and the airplane basically replaced the gear doors and was flying again in a couple days. Great stuff. Probably a good stock tip. There's one FAA-approved EMAS manufacturer in New Jersey, and you can Google it and figure all that out yourself. But that's what we're trying to avoid with this runway safety area. You can't have anything in that rectangle run, that runway, 500 feet either side of, or 250 feet either side of center line, and 1,000 feet off each end. So that's declared distances. So Next module is going to be the wet runway takeoff performance module.
Wet runway takeoff performance. Takeoff performance on a wet runway presents a unique challenge to transport airplane pilots. In this program, we will review the certification history for accelerate stop distance and takeoff distance, the differences between wet runway and dry runway performance, and key points for performance planning for taking off from a wet runway. A requirement of transport airplane performance planning is determining that the takeoff can be safely conducted on the length of runway declared usable for takeoff. The certification rules for these airplanes prescribe 3 distances that must be considered: the accelerate stop distance, the takeoff distance, and the takeoff run. Of particular importance is accelerate stop distance, or the distance required to accelerate to a point in the takeoff, then in response to an event, take the first action to reject the takeoff at a speed no greater than V1 and to bring the airplane safely to a stop. Originally, the accelerate stop distance did not include consideration for events other than engine failure that could lead to a rejected takeoff. In 1978, the certification rules were amended to consider both engine failure and non-engine failure scenarios. Accelerate stop distance was revised to be the longer of the distance with one engine failing just prior to V1 or with all engines operating throughout the rejected takeoff. However, accelerate stop distance was still determined only for a dry runway. In response to the disproportionate number of rejected takeoff accidents on wet runways, the certification rules were again amended in 1998. Manufacturers are now required to provide wet runway accelerate stop distance and wet runway takeoff distance data in the airplane flight manual for all newly type certificated transport airplanes, and the operating limitations and rules require the use of this data when the runway is wet. Typically, the minimum field length required for takeoff in a 2-engine turbojet transport category airplane is based on the balanced field length concept, where the accelerate stop distance is equal to the 1-engine inoperative takeoff distance. The balanced field length can be obtained when, for a given takeoff weight, a V1 speed is selected such that these 2 distances are equal. When the runway is wet, the accelerate stop distance increases due to reduced friction during braking. The braking friction on a wet runway varies greatly with speed, while it is essentially constant with speed on a dry runway. At faster speeds, the wet runway braking friction is much lower than at slower speeds. The reduction in braking friction is partially offset by the stopping performance credit permitted for the use of thrust reversers on a wet runway if they are installed and operative. On a dry runway, the 1-engine inoperative takeoff distance ends when the airplane reaches a height of 35 feet above the runway. To reduce the V1 speed to both rebalance the probability of rejecting a takeoff on a wet runway versus continuing that takeoff and to reduce the speed at which braking would be attempted, the regulations allow us to consider that the wet 1-engine inoperative takeoff distance is complete when the airplane reaches 15 feet rather than 35 feet required for a dry runway. Reducing this screen height also reduces the 1-engine inoperative takeoff distance on a wet runway. The allowance for reverse thrust credit and the use of a 15-foot screen height help the engineers rebalance the takeoff field length required for takeoff on a wet runway through the use of a lower wet runway V1 speed. The ability to reduce V1 speed can be limited by VMCG speed and the lowest permissible V1 speed in relation to this ground minimum control speed. When V1 speed is limited by VMCG speed, the takeoff on a wet runway will be accelerate stop limited. Note that the all engines operating takeoff distance for a wet runway remains unchanged from that for a dry runway. The all engines operating takeoff distance screen height for a wet runway remains at 35 feet and still must include the 15% margin. In most cases, the maximum allowable takeoff weight on a wet runway will remain less than the allowable weight on a dry runway, even though the wet runway case includes credit for available reverse thrust and reduced screen height. However, there are exceptions. Rocky Mountain Regional Airport, better known by most as Jeffco, presents an interesting wet runway example for some turbojet airplane types. Runway 11 left, 29 right is the primary runway used by jet airplanes. Runway 29 right is 9,000 feet in length. The runway also has an upslope of 1.2%. A check of a takeoff analysis for one particular business jet type finds that the takeoff weight limit on a wet runway at 20 degrees Celsius appears to be 36,030 pounds. On a dry runway for this same airplane type, the maximum takeoff weight is 33,840 pounds, or almost 2,200 pounds lighter than the apparent weight limit previously calculated on a wet runway. At 33,840 pounds, the balanced field takeoff distance is precisely 9,000 feet, the length of runway 29 right. However, at this same weight, the balanced field takeoff distance on a wet runway is only 8,000 feet. The reduced screen height and credit for use of thrust reversers determining the wet runway takeoff performance can in some cases actually produce a situation where at a given takeoff weight, the wet takeoff performance appears to be better than the dry runway performance. This can lead to a situation where the wet runway analysis produces greater takeoff weights than the dry analysis, but the certification rules have an additional requirement to address this situation. These rules specify that the accelerate stop distance and the one engine in operative takeoff distance must be the greater of either the dry runway or wet runway distances. This requirement is reflected in the instructions furnished in most FAA-approved airplane flight manuals, where wet runway takeoff performance data is furnished. Users are advised to check the distances required or takeoff weight limits determined on a wet runway against those for a dry runway condition and to use the most restrictive distance or weight limit. In some instances, the airport analysis furnished will incorporate this dry check. However, users should verify this feature with their performance engineering services provider for their aircraft. While the scope of this discussion is focused on takeoff performance planning, pilots of transport category airplanes should also be familiar with the takeoff safety training aid. The goal of this aid is to reduce the frequency of rejected takeoff accidents through improved pilot knowledge and awareness of the factors affecting the successful outcome of the go, no-go decision. The takeoff safety training aid may be viewed at the FAA's Airline Operator Training website. In summary, when performing departure planning from a wet runway, pilots should have a general idea what the effects of this wet surface will have on accelerate stop distance and takeoff distance. Operators should ensure that the evaluation of the takeoff weight limit for both wet and dry conditions is performed, and that the most restrictive weight, the lighter weight, is used for takeoff and that a wet runway V1 speed is used. This is true whether manual computations are being performed by the pilots or vendor-provided takeoff computations are being utilized for departure planning.
Okay, the next module, and we're going to take a break, but I hope this will keep you coming back, is we're going to talk about landing distance assessments. And you may remember several months back a Air Force C-17 coming from Afghanistan after about 18 hours of flying and 2 refuelings, and it had a 4-star general in the back sitting in his Airstream trailer in his VP quarters. They were cleared into the MacDill airspace to land at Tampa, and took the visual and put the C-17 into Peter O'Knight Field, which, if you're familiar, is on the other side of that little hook, that little bay there. And there was a guy standing out there with his iPhone that got it on short final. So here comes the C-17. I think it's about a 4,200-foot runway, 4,300 foot or so. And they landed at the wrong airport, and it wasn't pretty.
Oh my God.
Yeah. Oops. So he jumps on the binder.
Oh no. Oh my God.
He stopped at about 2,200 feet. Pretty good airmanship, except for the
He stopped on that.
The four-star in the back had
No
the
way.
chief of staff of the Air Force on his speed dial. And he hit it, and he said, "Nick, they got me to Florida. Unfortunately, it's the wrong airport."
I was looking at it coming over. I was like,
So those guys had a little bit of explaining to do. I can't believe not flying that long and being that tired and not hooking up to the ILS and letting the autopilot take me in. But anyway, it didn't happen. Wasn't me. Thank God I wasn't there. But the airplane was out of there shortly. Okay.
Landing distance assessment, understanding the regulations, and preventing overruns. This module discusses landing distance assessments for a transport category turbine-powered airplane and how they relate to the landing distance available, or LDA. As pilots progress from smaller equipment to larger, more complex airplanes, landing distance determination becomes a much more important facet of airplane performance. Unfortunately, landing overruns continue to occur. One important aspect of minimizing these events is for flight crews to gain a more complete understanding of landing performance. This module will review two different and unique landing distance calculations. For identification purposes, we will refer to these as pre-departure planning and time of arrival landing assessment. The landing distance for a transport category airplane is defined by the certification rules in Part 25. This certificated landing distance starts at the point where the airplane main wheels are 50 feet above the runway surface. It continues through a nominal air distance and includes time delays, allowing for the transition into the stopping configuration. The landing distance ends at the point where the airplane comes to a complete stop. The use of deceleration devices, such as normal wheel brakes with anti-skid action, spoilers, and lift dumping systems, may be used in determining the landing distance. However, the use of thrust reversers is not considered when calculating the certificated landing distance. Landing distances based on these certification rules reflect the maximum capability of the airplane and are generally shorter than the landing distances achieved in normal operations. Prior to 2002, the certificated landing distance was based on a stabilized approach at an approach speed not less than 30% above the stalling speed in the landing configuration, or 1.3 VSO. A speed greater than 1.3 VSO could be used if needed for acceptable airplane handling characteristics. Over the years, this final approach speed became known by the term VREF, or Landing Reference Speed. However, this particular V speed was never part of the certification rules. Beginning in 2002, the term VREF was officially incorporated into the Code of Federal Regulations as a defined V speed. Since this change occurred at the same time the rules governing stall speed calculation were amended, VREF differs slightly from its previous use. VREF as now defined may not be less than the reference stall speed, or VSR, which is the speed at which the stall speed in 1G flight corresponds to the point of maximum lift coefficient just before the lift starts decreasing as angle of attack is further increased. VREF must also be above the landing minimum control speed and any speed necessary to demonstrate acceptable airplane handling characteristics. With the adding of VREF to the regulations, the rule defining approach categories was also amended. For airplanes where VREF is defined by the certification rules, the approach category for that airplane is based on its VREF speed determined at its maximum certificated landing weight.
Stop here just for a second because I want to emphasize something. FAA just recently released a safety information for operators on this whole topic. And the issue is this, is that if your airplane is a Category C airplane, you have to fly the Category C approach minimums. You can't fly between 91 and 121 knots because you're lighter, fly slower, and fly Category B minimums. Because the rule requires that you fly at 1.3 VSO at a maximum certificated landing weight or VREF at maximum certificated landing weight. This has come up a lot with the airline community and the Part 91 community in the last couple of years. And the reason for that is if you're a Category D airplane, Yeah, you can fly slower. You could fly Category C speeds, but if you go missed approach, you are going to be flying back in your Category D speeds, and you don't have the obstacle clearance on the missed approach that's published for that particular procedure. So I think it's very important that everybody understand that. You can always fly faster if you have a no flap, for example, or you can fly circling airspeeds or something like that. But the point is, if you're, and how do you determine that? Well, you have a limitation section in your AFM that says the max certificated landing weight for this airplane is X, and you find that X, and then you find out what category you're in. It doesn't necessarily or will not say in the AFM you're a Category C or a Category D airplane for approach purposes. So, you know, we have an issue right now where we have a Learjet operator, for example, based in an airport in Iowa with his airplanes there, and he has no Cat C minimums for that airport. So they were flying the approaches at Category B speeds. And, you know, we presented this at the Bombardier's stand down, and he came to me and said, you mean to tell me that every instrument approach I shoot at my home drome, my home airport, is illegal? And I said, that's correct. So we're trying to figure out ways, we cannot waive it. We're trying to figure out ways to get Category C approach speeds for those GPS and RNAV approaches they have out there. And we think we actually have a way to do that. And we're going to, but you know, when you start talking about amending approaches, it goes in the queue, and we're not going to be able to get them those charts published until next May, unless we do something different. So we're working on those kind of things. So if you're in that kind of situation, beware that that this thing applies. It's pretty critical.
The landing distances determined during certification are established with full awareness that operating rules require additional factors to be added when determining the minimum operational field lengths for landing during normal line operations. The operating rules for Part 121, Part 135, and Part 91K require that the landing distance demonstrated during certification remain within a specified percentage of the runway length available for landing at both the destination and alternate airport. As a result, these rules establish a minimum operational field length for landing. This requirement does not apply to Part 91 operators, but voluntary adherence to these rules is encouraged. These operating rules impose a limitation on takeoff weight, such that you do not plan to arrive at your destination or alternate airport at a weight that will not allow you to meet the landing distance requirement specified in the operating rules. Therefore, any planning intended to demonstrate compliance with these rules must occur prior to takeoff, or as condition of dispatch for those operators subject to dispatch requirements. When required by the operating rules, the landing distance demonstrated during certification must permit the airplane to come to a full stop within 60% of the landing distance available. Another way of saying this is that the landing distance demonstrated for certification must be multiplied by a factor of 1.667, or divided by 60%, to define the factored landing distance on a dry runway. The resulting factored landing distance is intended to account for operational variables, including piloting techniques, flight path deviations, tire and brake wear, atmospheric conditions, including gusts, and other variables not addressed during landing distance certification. For eligible Part 135 and Part 91K operators, the landing distance demonstrated during certification must permit the airplane to come to a full stop within 80% of the landing distance available. In this case, the demonstrated landing distance for certification is multiplied by 1.25, or divided by 80%, to obtain the factored landing distance on a dry runway for these operators. Landing distance data that is published in the Airplane Flight Manual varies widely between airplane manufacturers. Some manufacturers furnish the landing distances determined during certification, in which case pilots are expected to apply the appropriate multiplier 1.667 or 1.25, while others furnish the factored landing distance data for use in complying with the operating rules. Some manufacturers provide both the certified and factored landing distances, as in this example. A few manufacturers do not provide landing distance data at all, but rather provide data on the maximum allowable landing weight as a function of landing distance available. Let's use the data we just looked up to perform our pre-departure landing distance evaluation. At 19,200 pounds, the landing distance determined during certification is 2,700 feet, and the factored landing distance is 4,500 feet. Since the landing distance available is 5,000 feet, the runway length is adequate provided the runway is dry. However, if the runway is expected to be wet or slippery at the time of arrival, the operating rules require that the dry runway factored landing distance be increased by an additional 15%. In this example, our factored landing distance increases to 5,175 feet. Therefore, a 5,000-foot runway that is wet is no longer of adequate length for a planned landing weight of 19,200 pounds. It is important to note that this additional 15% increase is not based on demonstrated wet runway stopping performance. Therefore, the wet runway factored landing distance may not provide the additional distance necessary to accommodate actual stopping performance on a wet runway, let alone a runway contaminated by snow or ice. The factored wet landing distance exceeded the landing distance available, so we cannot legally take off. We will need to reduce the planned landing weight. If we multiply 4,300 feet by the wet runway factor of 1.15, the resulting distance is shorter than the landing distance available. Therefore, our takeoff weight must be reduced to a value that permits a landing weight not in excess of 18,000 pounds. Many runways used by transport category airplanes have skid-resistant surfaces, which may include runway grooving, porous friction course overlays, or a combination of both. Runway grooving and PFC surfaces allow water to escape from beneath the aircraft tires traveling at high speed, which reduces the threat of hydroplaning, but does not eliminate it. These surfaces do not drain water from the runway, nor do they increase the friction capacity of the runway surface. A common misconception is that a grooved or PFC runway is considered to be dry for the purposes of applying the 15% increase when the weather reports or forecasts indicate that the runway may be wet or slippery at the time of arrival. Unless otherwise approved by the FAA, if the weather reports or forecasts indicate that the runway will not be dry at the time of landing, then the 15% increase to the factored landing distance must be applied. The intent of this pre-departure planning is to ensure that a flight operation does not begin that cannot reasonably be concluded upon reaching the destination or alternate airport. Pre-departure planning is required by Part 121, Part 135, and Part 91K operators. Part 91 operators are encouraged to do so, but it is not required by the operating rules. At the destination airport, the factored landing distance must be evaluated using the most favorable runway, usually the longest runway in still air conditions, and for the most suitable runway for landing in consideration of wind conditions, instrument approaches available, or other factors that make use of this runway desirable. The evaluation of the most suitable runway is not required when an alternate airport with a runway that meets both of these requirements is designated. These same requirements apply to the alternate airport if one is required. This evaluation is adequate for landing performance planning for routine operations when the runway is dry. The 15% increase required when the runway is wet or slippery is not based on demonstrated stopping performance, but is an arbitrary additive applied to the dry runway factored landing distance. The factored landing distance calculated during pre-departure planning is not a limitation at the actual time of landing. A runway may be used for landing when the factored landing distance exceeds the landing distance available published for that runway. However, an assessment of actual landing distance is recommended. More on that subject in a moment. It is especially important for flight crews to understand that the landing distance data established during certification and published in the AFM is not representative of everyday operational practices and does not reflect operational landing distances. This is true even when the AFM or QRH labels such data as actual landing distance, as shown in our previous example. This is because not all operational factors affecting landing distance are required to be accounted for by certification regulations. The landing distances determined during certification are aimed at achieving the shortest landing distance possible with a test pilot at the controls. To achieve the minimum airborne portion of the landing distance, flight testing and data analysis techniques can result in assumed touchdown rates as high as 480 feet per minute. The approach angle flown during testing may be steeper than the approach angles typically flown on an ILS or visual approach. To minimize the ground portion of the landing distance, the test pilot initiates maximum manual braking as soon as possible after touchdown and continues using maximum braking until the airplane comes to a complete stop. These flight test techniques are not typically practiced by flight crews during normal landings. The certification rules for landing distance data do not require correction factors for runway slope or for non-standard temperatures, and do not normally account for the use of auto brakes, auto land systems, or thrust reversers. However, some manufacturers may provide correction factors for runway slope and non-standard temperature with the knowledge that the AFM landing distance data, as determined during certification, may be used by pilots to assess landing runway requirements during normal line operations. Nevertheless, it is easy to appreciate that the landing distances determined during certification and the certificated landing distance data published in the AFM will be shorter than the actual landing distances achieved in everyday operations. Flight crews may mistakenly assume that the large regulatory margins built into the pre-flight departure landing checks are always adequate to protect against overrun in any potential landing conditions encountered. This perception is dangerously inaccurate. FAA and NTSB data identifies failure to assess actual required landing distance to account for slippery or contaminated runway conditions or any other change condition existing at the time of landing as a significant causal factor in landing overruns. Let's look at a hypothetical landing performance planning example using Chicago's Midway Airport. The pre-departure landing analysis includes a review of current and forecast weather at the destination airport and the alternate airport, and a determination if the landing weight upon arrival will permit the factored landing distance to be less than or equal to the landing distance available. The operator must evaluate the longest runway in still air conditions. They must also evaluate the most suitable runway given the weather conditions and approaches to be used unless an alternate airport is designated. Using Chicago Midway as our destination airport, for our estimated time of arrival, Runway 13 Center is both the longest and the most suitable runway, given the forecast weather and the ILS approach to this runway. The results of this analysis may be presented to the flight crew in the form of a maximum allowable landing weight on a particular runway. For Runway 13 Center, our maximum allowable landing weight is 19,200 pounds. Another option available is to use the data and procedures provided in the airplane flight manual to determine the dry or wet runway factored landing distance required at the airplane's estimated landing weight. The dry or wet runway factored landing distance, as applicable, must not exceed the runway's landing distance available. This pre-departure planning does not ensure that the airplane can safely land on the runway in use at the time of arrival.
Chicago Midway Information Romeo 2251 Zulu. Wind 150 at 7. Visibility 3 miles. Rain. Ceiling 600 broken. 1,500 overcast. Temperature 2. Dew point 0. Altimeter 29er 89er. Approach in use ILS runway 31 center. Landing and departing runway 31 center.
FAA SAFO 06012 recommends that all turbojet operators have procedures to ensure that a full stop landing with at least a 15% safety margin beyond the actual landing distance can be made on the runway to be used in the conditions existing at the time of arrival and with the deceleration means and airplane configuration that will be used. While this assessment does not mean that a specific calculation must be made before every landing when conditions deteriorate or the landing runway changes from the planned runway used in pre-flight planning, a calculation or other method of determining the actual landing distance capability should be accomplished. This assessment can take many forms. One example would be determining before the flight that you can land with at least a 15% safety margin on the planned arrival runway at maximum landing weight in the planned landing configuration with 10 knots of tailwind in any runway braking condition better than poor. Your assessment at the time of landing may be as simple as verifying that the landing would be conducted within those parameters. This landing distance assessment should be accomplished as close to the time of arrival as practical, taking into account workload considerations during critical phases of flight and using the most up-to-date information available at the time. pilots should also look beyond the current conditions and plan for the worst-case conditions. Additionally, operators should use the most adverse reliable braking action report if available, or the most adverse expected conditions for the runway, or portion of the runway that will be used for landing when determining the landing performance assessment. When conditions are such that the runway surface conditions vary along the runway, such as braking action fair first 2/3 but poor the last 1/3, then the most conservative or worst condition for the portion of runway to be used should be used for the landing distance assessment. Based on the ATIS information received, what would you consider when performing a landing distance assessment? At a minimum, we should consider the operational impacts of the wet runway and the tailwind. The assessment may be based on manufacturer-furnished advisory landing distance data for use on wet and contaminated runways. This data is an analytical computation that adjusts landing distances determined during certification for the detrimental effects on braking performance resulting from a particular type of contamination. While the data is not based on actual flight testing, it does allow flight crews to assess actual landing performance based on the anticipated landing conditions. Once the actual landing distance is known, SAPO 06012 recommends that a 15% safety margin be added and that the resulting distance be less than the declared landing distance available, unless imminent risk to continued flight makes this landing imperative. For those airplanes where advisory contaminated runway landing distance data is not available, SAPO 06012 provides factors based on the reported runway condition or braking action reports to determine the minimum runway required for landing. These factors are applied to the factor dry runway landing distance used in pre-departure planning and include the recommended 15% safety margin. After this initial landing distance assessment is complete, pilots should monitor for deteriorating runway conditions prior to landing and base their decision to continue on the most conservative assessment of the aircraft's stopping performance on the runway. In some cases, contradictory information concerning runway conditions or braking action reports may force the flight crews to apply their best judgment about which information is likely to be most accurate. The receipt of new or updated information on runway conditions may result in the reevaluation of a previous decision to land. In a case where uncertainty of landing distance remains, it may be appropriate for the pilot monitoring to quickly reference the QRH or tab data, or in other cases, the prudent use of a go-around and a holding pattern at a safe altitude to reevaluate the decision to land or divert may be the best decision.
Citation 938 Sierra Charlie, cleared to land, runway 31 center. Wind 140 at 8. Reported braking action fair touchdown, poor rollout.
Based on the previous time of arrival landing assessment, but now with a report of deteriorating runway conditions, what would you do? Operators of turbojet airplanes are encouraged to develop standard operating procedures for flight crews to assess landing performance based on the runway conditions actually existing at time of arrival. Ultimately, it is up to the crew, based upon the amount of time, type of tools, and information available to them, to decide the most appropriate time to accomplish this assessment, and how detailed it must be based on the situation facing them. For more information on this important topic, flight crews are encouraged to review Safety Alert for Operators 06012, Landing Performance Assessment at Time of Arrival, and Advisory Circular 9179, Runway Overrun Prevention.
Okay, that's the module and landing distance assessments. Notice we draw the distinction between pre-departure planning and when you're in the air and actually things change. So that's particularly true, I think, in the Part 91 community, where the boss in the back wants to go somewhere else after he gets airborne, and now you've got to scramble to make those kinds of decisions. Any questions for experts here on the landing distance assessments? Yes, sir.
Still using the definition of wet runway as a reflected runway, even for crew?
A wet runway is when it's not a dry runway. That's all I know.
It's based on the weather forecast, too. I know you'll see some that says a wet runway is one that is reflected.
That's a definition. It's been in several different flight manuals. It's been in the EASA, the previous to EASA, the JAA regulations and such. We've been trying to change that for quite some time. That the data actually show that even if a runway is only what you would term as damp, that it's more, that the effect on braking is more like a wet runway than it is like a dry runway. It's more than halfway toward being a fully soaked runway. So anytime the runway is not dry, basically, whether it's grooved, PFC, smooth, whatever, you should consider that runway to be wet for performance.
And I know, I remember we had some incidents at Seattle at certain sun, setting times where it was just like a mirror. And the guy says, is this runway wet or is it dry? And, they were trying to make those kinds of decisions. It gets very confusing. But our point is that if it's got anything on it at all, it's wet. Otherwise, it's dry. A lot of people think that the groove runways and these porous runways, they don't do it. They help you with tire friction and so forth and draining of water for sure, but it's going to be an issue that we can talk about for years to go.
How come we don't come up with something like the military? I spent 20 years in the military, and we had the
Yeah.
RCR. And,
Yeah.
if it was 23, it was dry. If it was 12, it was wet. And
RCR,
factor in something-
runway condition rating.
It was very, very simple, and everything. Was
Yeah, I know. And Roy participated on the Talpa Arc. I don't know if you've heard of that group, but after the Midway accident, the FAA just jumped through all kinds of hoops and said, "Oh my God, we got to come up with all kinds of new regulations for these runway assessments." And it became operationally just almost impossible to do. I mean, there were some real showstoppers there, and one of the issues that they looked at were mu meters and all these gadgets that came up in Europe, and there's been a lot of, and they couldn't get standard calibration on them, and some of them didn't work, and it's been a very, very difficult issue.
And at the end of the day, landing at an uncontrolled airfield it's a best, I guess.
Yeah, and we've all had those experiences. I remember, when I was flying and going into Rochester, ever a particularly tough 3 or 4 days of winter snow, and we landed at Rochester. And I remember when we broke out on the ILS, it was like looking at a tunnel of snow, and I was in a little Piedmont Airlines Fokker 28. It had these big spoilers on the tail that open up, so it just quit flying when you get on the ground. And the tower says, "Congratulations, Piedmont, you're the first airplane to land here in 3 days." And I said, "Well, thank you very much, sir." Yeah, and then the other issue is if the guy, when you're on short final and the guy in front of you said, "I report the runway condition is nil," then there's other issues there too. But I don't know if you want to comment on any of that Talpa Arc business. But
Well, one of the recommendations of the Talpa Arc actually was to go to a numeric system, like you're mentioning, a 1 through 6, a takeoff on the ICAO standard today. But the key to it is to get standardized reporting, and the Talpa Arc recognized that, and we put together some pretty good recommendations that the FAA has been involved in 2 years of testing with Alaska Airlines in real-world environment to prove them out. So I think we're approaching the point at which we think we have some better methods that could be rolled out.
thank you. Okay, with that, we're going to play the. How many folks in here have ever lost an engine in a jet airplane on a takeoff? 1, 2, B-52. Yeah, that had 8. That doesn't count. I lost 18 in a C-123, but that surely doesn't count. Those things, but yeah. So these engines are phenomenal machines. I mean, they just don't fail very often. I've got an old buddy of mine named Sully Sullenberger that put that thing in the river up there a couple of years ago, and he was an Air Force fighter pilot, and his whole career he never lost an engine. And then I emailed him and I said, "Sully, he's 56. I said, you need to retire because you've just got rid of every piece of luck in your body and it ain't coming back." And he sent me back. He said, that's the first time I ever lost 2 engines in my life. Didn't say 1, 2, and he only had 2. So, yeah, it's very, very rare occurrence. But boy, I tell you what, bird strikes, and we got a video here. I've had bird strikes. I think everybody has flown airplanes for any length of time has had bird strikes. You get one like this guy got. Here's the birdie. Plunk, 757 in the UK. And there he goes. And that could happen to anybody. That's probably the most common cause of an engine failure on takeoff. So this is a British airline that took off in the 757, and you know, these airplanes are magnificent. They fly on one engine just fine and everything, but it's an emotional experience, you know. I was always taught, and I think any good pilot should think of, on every takeoff, I'm going to lose an engine on this takeoff, or what do I do if I lose an engine? And I don't know if that mindset is carried off to the younger folks in this business or not, because they're so reliable. But the fact is, when you get into places like Aspen and Jackson Hole and you know, Eagle, places like that, you've just simply got to be thinking that way. So this final module is on departure planning, and particularly on SID climb gradients and one engine and operative planning. Like I showed you at the beginning of the presentation, we in the airlines were spoiled. We had these beautiful charts, and we could put stuff in the flight management computer and fly these things out in the autopilot. And it could be a real issue for some of the Part 91 folks.
Flight planning is an important activity of every pilot. A critical element is careful consideration of the airplane performance capabilities for the airports used for takeoff and landing. This is especially true for the takeoff, since the airplane is often near its performance limiting weight. Every pilot is aware that the length of runway available for takeoff significantly influences the maximum allowable takeoff weight. But what lies beyond the runway may be of equal significance. Planning for takeoff obstacle clearance in transport category airplanes. Obstacle clearance is an important element in transport category airplane performance planning. This module will review the relevant certification rules, the operating rules, and FAA guidance for assessing takeoff obstacle clearance in transport category airplanes. Takeoff obstacle clearance planning often presents its greatest challenge at mountain airports. The airport at Aspen, Colorado, located in the Rocky Mountains, serves as an excellent example with which to explore this challenge. Let's listen in as a flight crew briefs their flight plan from Aspen to Atlanta, taking into consideration one engine inoperative.
I would think the first thing we need to look at is the runway out of Aspen. So I have that right here. And taking a look at the runway, it looks like it's 8,006 feet long, but there is a displaced threshold. So let's go see what that's all about and make sure there's no limits there. When you look at the numbers right there, it says the last 1,000 feet is not available for landing distance computations in the note. Well, we're not landing there, we're taking off, so that's not going to be a huge issue for us. No big deal there. We're also going to be using the lens departure procedure, and it has weather minimums on it, which are, I believe, 400-foot ceiling and 1 mile visibility. Is that correct?
That's correct.
Okay. And a minimum climb gradient. Do you have any questions about that?
I don't think we're going to be able to meet that climb gradient single engine.
No, we won't. 2-engine, not much of a problem. We can look that up and verify it. But 2-engine, we can meet it. Single engine, we won't. So we're going to need another plan.
This flight crew has accomplished a thorough review of the performance challenges affecting their planned departure from Aspen. Now let's take a moment to examine the challenge of takeoff obstacle clearance and avoidance planning when departing Aspen. A review of the certification rules regarding the takeoff path is a good place to begin our discussion. The certification rules define a takeoff path or vertical profile that is used to establish both the takeoff climb limit weight and the takeoff flight path for determining the takeoff obstacle limit weight. The takeoff path is divided into a series of segments. Let's examine each of these segments in greater detail. The takeoff path begins from a standing start. The critical engine is failed at VEF and remains inoperative for the rest of the takeoff. The first segment begins at liftoff and continues until the landing gear is fully retracted. The airplane is accelerated in the air to V2 speed. During this segment, a turbine-powered airplane with 2 engines must be capable of achieving a positive climb gradient in still air with 1 engine inoperative and without the benefit of ground effect. Additional climb performance is required for airplanes with more than 2 engines. The second segment begins once the landing gear is fully retracted. The airplane must once again demonstrate a minimum climb gradient in still air with 1 engine inoperative. For a turbine-powered airplane with 2 engines, that minimum climb gradient is 2.4%, which is determined at the point where the landing gear is fully retracted. Additional climb performance is required for airplanes with more than 2 engines. The first and second segment climb is based on flying V2 speed. However, it is important to understand the significance of this speed. If the engine fails at the most critical point in the takeoff at VEF, which is reached just before V1 speed, and the pilot, electing to continue the takeoff at V1, rotates into the target engine failure takeoff pitch attitude, the airplane will attain V2 speed at the point that the airplane attains a height of 35 feet above the runway. If the engine failure occurs above V1, many AFM procedures recommend rotating to the same target pitch attitude. As a result, the speed obtained at 35 feet will be higher than V2. These procedures recommend maintaining this higher speed up to a maximum of V2 plus 10 to V2 plus 20 knots, when such an increase does not affect climb performance. The second segment must continue to a minimum height of 400 feet above the runway surface. No changes are allowed to the airplane's configuration or thrust while maintaining a speed not less than V2. The climb gradient during the second segment will gradually diminish due to thrust decrease resulting from increasing true airspeed and reduced air density as the airplane gains height. Therefore, the climb gradient capability will be greatest at the beginning of the second segment. Once the airplane has achieved at least 400 feet above the runway surface, the transition segment may begin. During this level flight segment, the airplane is accelerated to flap and slat retraction speed and then to the final takeoff airspeed. The transition segment ends when the airplane is in the clean en route configuration at an airspeed of not less than VFTO and when the remaining engines are set to maximum continuous thrust. If the airplane is less than 1,500 feet above the runway surface at the end of the transition segment, then the final takeoff segment begins at that point and extends until the airplane reaches at least 1,500 feet. At any point above 400 feet, a turbine-powered airplane with 2 engines must be capable of achieving a minimum climb gradient of 1.2% in still air. Additional climb gradient capability is required for airplanes with 3 or 4 engines. Over the years, the airspeed flown during the final segment has been referred to by a number of different terms. You may be familiar with VFS, VENR, or VSSE. In 2002, FAA incorporated the term VFTO, or final takeoff speed, into the certification rules to identify the airspeed to be flown in the final segment. This speed provides an adequate margin above the stall speed in the clean configuration. Here we see the complete takeoff path from brake release until the minimum height of 1,500 feet above the runway surface. It is helpful to think of these minimum climb gradients imposed by the certification rules as a mandatory minimum level of the airplane's surplus energy condition during takeoff. This surplus energy can be used for either climb or acceleration, or some combination of the two. Since these climb gradient requirements are based on airport temperature and pressure altitude, they are not runway specific. However, choosing flap settings for a given takeoff can affect the climb limit weight. Increasing flap settings used for a takeoff reduces the runway length required for takeoff in most cases. However, it also decreases the takeoff weight limit at which these minimum gradients can be achieved. Depending on the runway choice available for takeoff, this interrelationship effectively means that the climb limit weight may be runway specific. These climb gradient requirements are intended to provide a minimum acceptable level of one engine inoperative climb performance, but are definitely not intended to satisfy obstacle clearance requirements. Obstacle clearance must be considered separately. The requirements for takeoff obstacle clearance may be found in Subpart I of Part 121 and Subpart I of Part 135 of the Code of Federal Regulations. Looking back at the operating rules for an airplane like the DC-6 or Lockheed Constellation, following an engine failure on takeoff at V1 speed, the airplane was required to clear obstacles by 50 feet at any point until the airplane's actual height above the runway was 1,000 feet. In the 1950s, it was recognized that 50 feet of obstacle clearance after an engine failure was not sufficient to support the new generation of jetliners that were on the horizon. To provide adequate obstacle clearance for the new turbojet airplanes, the air carrier operating rules introduced for these new airplanes in 1957 provided an increasing margin of obstacle clearance as the airplane traveled further from the end of the runway. To provide this obstacle clearance margin, these new rules required that the takeoff path clear any obstacle by 1% of the obstacle's distance from the end of the runway plus 35 feet until the airplane was 1,000 feet above the runway. These rules proved cumbersome for operators to use and were quickly modified. As a result, they were applied only to early Boeing 707s. Beginning in 1958, the certification rules defined a separate takeoff flight path that begins at 35 feet above the runway surface at the end of the takeoff distance. It is a one-engine inoperative path that continues through each of the takeoff segments and ends when the airplane is at a height of 1,500 feet above the runway, or at the point at which the transition to the en route configuration is complete, whichever is higher. This actual or gross takeoff flight path represents the one-engine inoperative performance that the airplane has been demonstrated to be capable of achieving for a given weight, thrust configuration, and set of environmental conditions. To simplify the obstacle clearance analysis process, these revised certification rules also defined a new net takeoff flight path. The net takeoff flight path is determined by decreasing the airplane's demonstrated one-engine inoperative performance by a conservative margin. When required by the operating rules for turbine-powered airplanes, this net takeoff flight path must clear obstacles by 35 feet. For four-engine airplanes, the net takeoff flight path is defined by reducing the gross climb path by 1%, thus retaining the original 1% obstacle clearance margin required by the previous operating rules for the Boeing 707. For the level acceleration and flap retraction segment, the 1% regulatory gradient reduction is converted to an equivalent reduction in acceleration, resulting in a net third segment that is longer than the gross third segment distance. For three-engine jet airplanes, the regulatory gradient and acceleration reduction defining the net takeoff flight path is 0.9%. For two-engine jet airplanes, the regulatory gradient and acceleration reduction is 0.8%. Clearing an obstacle by 35 feet doesn't sound like much of a safety margin, but remember that the net takeoff flight path is defined as the actual flight path, often referred to as the gross path, minus the prescribed reduction in performance. The intent of defining obstacle clearance in terms of net performance is to provide a reasonable safety margin should the airplane's climb performance following an engine failure be less than predicted. These differences are due to the operational variations that can reasonably be expected in gross weight, thrust, airplane drag, pilot technique, wind effects, and so on. However, except during the level flight segment, there will be an increasing margin of obstacle clearance between the actual takeoff flight path following an engine failure and the net takeoff flight path used to assess the required obstacle clearance. For example, if a two-engine airplane is 10,000 feet beyond the start of the takeoff flight path at 35 feet during the second segment climb, the difference between the gross height and the net height will be 0.8% of 10,000 feet, or 80 feet. Thus, the requirement that the net takeoff flight path must clear the obstacle by 35 feet means that the airplane will actually clear the obstacle by as much as 115 feet. As noted previously, variables that may reasonably occur during normal operations may reduce this margin. The takeoff flight path and net takeoff flight path begin at 35 feet above the runway surface. For airplanes with FAA-approved wet runway takeoff data, this can result in lower than normal obstacle clearance in the event of an engine failure on takeoff near V1. Because the airplane is allowed to be at a height of 15 feet above the runway surface, at the end of the one engine in operative takeoff distance for a wet runway, the airplane can be 20 feet closer vertically to the obstacle after taking off from a wet runway compared to taking off from a dry runway. Of course, if there is no engine failure during takeoff, there is no difference in the flight path of the airplane taking off from a wet runway compared to taking off from a dry runway. The airplane manufacturer is required to furnish performance data and procedures for use in assessing net takeoff flight path obstacle clearance. The airplane manufacturer has significant latitude in the design and presentation of this data, including providing it in an electronic format. In addition, the procedures used for constructing the net takeoff flight path and the nomenclature used on the data charts may vary widely between manufacturers. While the complex array of charts typically provided in the airplane flight manual satisfies the regulatory requirements, most pilots would find it impractical to use these charts for routine departure calculations. The days of pilots calculating takeoff obstacle clearance from pages of paper charts in transport category airplanes are long gone, and for good reason. Today, the options furnished by the manufacturers to optimize the performance capabilities of these airplanes are very complex. The obstacle data sources that must be considered have grown in number, as well as the sheer number of obstacles that must be considered in any net takeoff flight path analysis. It is no longer considered feasible or practical to expect pilots to determine a takeoff weight limit for obstacle clearance on their own. Rather, it is expected that the analysis is completed by a professional aircraft performance engineer or a performance engineering provider, with the necessary training and resources available to make full use of data provided in the airplane flight manual. In addition, they are expected to collect and maintain an obstacle database using the best and most current data sources available for use in performing the analysis. In many cases, electronic performance data is now being provided by manufacturers, and in some cases the flight manual performance data is no longer provided in paper form. Performance engineers will most often use the airplane flight manual data to create a more practical means for pilots to evaluate obstacle clearance to support flight operations. Examples might include a software performance calculation tool, such as might be installed in an electronic flight bag, or a runway-specific airport analysis, summarizing the limitations for departure from a given runway. However, even these tools are dependent on a properly maintained obstacle data set. Regardless of how the analysis is prepared and presented, there are a few important items that all pilots should know about the net takeoff flight path obstacle clearance analysis. The airport runway analysis prepared by the performance engineer provides the pilot with the maximum allowable takeoff weight in consideration of performance requirements for the takeoff airport and runways specified. Because the climb weight limit is not directly associated with departure from a specific runway, it is often shown in a separate location from the runway weight limit. In addition to the climb weight limit, a runway weight limit for each runway is provided on the analysis. The runway weight limit considers each of the performance requirements that may restrict maximum allowable weight when taking off from a specific runway. Among other things, this runway weight limit assures that the net flight path will clear all identified obstacles by the required margin along the departure path. When preparing the analysis, the performance engineer must consider the performance data and procedures for calculating the net takeoff flight path prescribed for each airplane type. The net flight path data for most airplanes allow a second segment climb to any height above 400 feet that is necessary to clear obstacles up to a maximum height that permits the cleanup and acceleration to VFTO speed to be completed within the time limitation on the use of takeoff thrust. For those runways where obstacle clearance is not a limitation, the operator often establishes a standard acceleration height, for example, 1,000 feet above the runway elevation. The acceleration height is provided on the airport analysis for each runway end. Leveling at this height may be required for obstacle clearance in one of the takeoff flight path segments. However, on some airplane types, the second segment net takeoff flight path data terminates at a gross height of 400 feet above the runway. When this is the case, the engineer must plan the transition segment obstacle clearance on the assumption that the pilot will level off and accelerate at that height. Therefore, the maximum allowable takeoff weight cannot be based on climbing higher than 400 feet above the runway. Still, other airplanes are capable of an extended second segment climb, where the airplane is assumed to continue climbing at V2 with takeoff flaps to the end of the takeoff thrust limit. The transition segment is then completed using maximum continuous thrust. To use this option, it must be demonstrated that the airplane is capable of meeting the minimum gross climb gradient requirement for the final segment at the designated acceleration height with takeoff flaps extended and maximum continuous thrust. Using data furnished in the AFM, the engineer determines weight limit additions or subtractions applied to the runway limit weight to account for headwind or tailwind component, non-standard atmospheric pressure, engine bleed and ice protection configuration, and so forth. In some cases, the corrections are tabulated as part of the airport analysis, and the flight crew must apply adjustments to the limit weights. To deal with the complexity of the obstacle clearance analysis, some pilots have tried to simplify it by thinking of it in terms of meeting a required climb gradient. For example, the standard 200-foot per nautical mile or 3.3% climb gradient used on IFR departure procedures. It is important to understand that the one engine inoperative climb gradient data furnished in the airplane flight manual represents a spot value or snapshot of the airplane's performance at a particular point in the takeoff path. Airplane climb performance diminishes as the airplane climbs due to thrust lapse rate loss and as true airspeed increases with height. While it may appear that acceptable obstacle clearance can be demonstrated using a rise over run analysis based on a spot climb gradient, in reality, that is not the case, since the first and second segment net takeoff flight paths are not a constant gradient. As we just mentioned, the gradient reduces as the airplane climbs due to thrust lapse rate loss and as true airspeed increases with height. In addition, there is often a marked difference in slope between the first segment and the second segment due to drag resulting from the landing gear retraction sequence. Typically, the only rise over run obstacle assessment found in the AFM is for the final segment. The final segment flight path does not have any large discontinuities in it since the configuration is constant throughout, unlike the initial portion of the takeoff flight path where the gear is in extended position in the first segment and in the retracted position in the second. The combination of these factors make it possible for determining a conservative gradient based on the distance to the obstacle for use in a rise over run obstacle analysis from the end of the transition segment through to the end of the final segment. As you can see from this graphic, a simple projection of a climb gradient does not ensure compliance with the obstacle clearance rules in the event of an engine failure. Any time that the yellow line showing the constant assumed net second segment climb gradient is above the red net takeoff flight path line, we cannot assume that the constant gradient method will provide the required obstacle clearance because it does not reflect the airplane's true net takeoff flight path.
Rob Root from Boeing is going to explain to you what this slide means.
Start with big picture before detail. So climb and obstacle clearance, completely separate. Don't even think about them together. But here's what a pilot might be inclined to do. So my twin engine airplane has to have a second segment gradient of 2.4%. That's 2.4 feet up for every 100 feet forward. So as long as the obstacle doesn't violate that line, I'm always okay, right? Well, that's what's represented by the dashed or the dotted yellow line there. That's assuming the airplane maintains a constant gradient equal to what the gradient is right at the point where the gear comes up. Well, let's talk about reality. Before that point, the airplane is in a considerably worse drag configuration, right? We have the gear down still. In fact, it could get worse before it gets better because we might have an airplane where the gear doors come open to allow the airplane to retract the gear. Where we're evaluating that second segment gradient, the gradient's actually worse. Okay, what about after that? Well, after that, thrust is going to lapse as we climb up in altitude, right? And it's also going to lapse to some degree because we're holding a constant indicated airspeed, V2, and yet our true airspeed is going up as we go up in altitude. So that's going to cause a loss of gradient too. So what we're trying to illustrate here, the blue line which is what we really think the airplane is going to do, is underneath that dotted yellow line. And that's a bad thing, right? Because we're assuming any obstacle underneath that dotted yellow line is good to go. And yet the blue line is what the airplane actually does. So what's the third problem, and maybe the biggest problem? We hit this level flight, acceleration and cleanup segment, right? So we have another limit we have to be worried about, which is how long can we hold takeoff thrust? And for a lot of engines, that's 5 minutes. So we need to pitch the airplane over, and typically level flight is assumed, and we need to get cleaned up so that we can bring the power back to maximum continuous before we start that final segment. Well, now you can see this is where that blue line, the real airplane flight path, diverges significantly from that best case assumption that we were making, right? And then in the final segment here, we're accounting for the fact that we have gear up, we have flaps up, we're at a different speed, we're at a different thrust, etc. So the big picture, the thing I want you to take away from this, climb and obstacle clearance, two completely separate subjects. Does that make sense? Yes, sir.
I know you're trying to represent that, from takeoff to 400 feet, but is there really an appreciable difference between 0 and 400 feet as far as loss of thrust and also transitioning from gear to the gear out? Yeah, I mean, we're talking percentage-wise. It doesn't seem really significant.
I hate to go back to those spaghetti charts that pilots don't like. But the next time you have one of those spaghetti charts out, you know, the one where all the lines start down in the corner and then they kind of diverge? Take your eye and put it next to the corner and sight along those lines on the chart, and you'll see they're not straight lines. And that, in fact, is exactly what that chart is showing you. It's showing you degradation in climb as you go up. Is it significant? Well, first of all, I can say it's significant enough that it would be illegal to ignore it, right, in terms of dispatch. But secondly, I would say for a close-in limiting obstacle, it could be a consideration. Probably a bigger consideration is that level off segment. And there's one other thing. The climb performance doesn't account for wind. So if we take off with, let's say, 10 knots of tailwind, well, the climb performance is the same. The obstacle clearance is considerably worse. So there's another variable not accounted for in climb performance, but that must be accounted for obstacle clearance.
My second question is it given that if we leave the flaps at whatever the takeoff setting is, it's presumed to be that that's going to be worst case second segment climb performance. It's better to take off with a minimum flap setting to basically enhance the performance of second segment climb, correct? Now, is there at some time where the distance to the obstacle, where those two meet and cross, and where would that average?
So I can't answer it specifically for any given airplane, but basically the question has to do with flap selection. And if all we're worried about is climb performance, as a general rule, a less deflected flap is going to give us better climb performance, right? Which will manifest itself as a higher climb limited weight. But the problem is obstacle clearance is not just about climb, right? Like the gentleman pointed out, it's also about how much runway does it take to get to V2. And for a less deflected flap, it's going to take more runway. And so as a general rule, for what we would call close-in obstacles, a more deflected takeoff flap that gets us off the runway sooner is probably going to result in a less restrictive obstacle limited weight. On the other hand, for more distant obstacles, taking a penalty in terms of field length, but climbing with a more optimum flap, a less deflected flap, is going to get us a better limiting weight over the distant obstacle. So the bad news is you really can't guess. The good news is we're starting to see a proliferation of real-time dispatch tools that take into account all of this, right? So there are tools available that will tell you what the optimum flap is for a given set of obstacles and give you all the right speeds to fly it. Any other questions? The big thing I want you to remember is this is more than just a simple geometry problem. So don't take the 2.4% or the 3.3%, draw a straight line, and conclude that you're safe with regard to obstacles.
Our discussion thus far has focused on how the net takeoff flight path clears obstacles by the required height, but we haven't discussed which obstacles must be cleared. To help answer this question, FAA released Advisory Circular AC 12091, Airport Obstacle Analysis. According to the operating rules in Part 121 and Part 135, any obstacles that are located 200 feet on either side of the flight path within the airport boundary, or 300 feet on either side after passing the airport boundary, must be cleared vertically by the net takeoff flight path. This advisory circular, released in 2006, provides guidance on developing obstacle analysis that meet the intent of this requirement by accounting for factors that may cause a difference between the intended track of the flight path and the actual track of the flight path following an engine failure. The AC provides methods that account for factors that may affect the actual ground track relative to the intended ground track, such as wind and available course guidance. This is accomplished by using an obstacle accountability area within which all obstacles must be cleared vertically by the net takeoff flight path. For an engine failure procedure that is centered on the extended runway center line, this area begins at the runway end and expands at a predefined rate until it is at a maximum width 2,000 feet either side of the intended track. For some runways, a straight-out engine failure procedure may not be possible or desirable in terms of maximum allowable takeoff weight. On these runways, a special engine failure procedure may be provided that takes the flight path of the airplane away from the terrain or obstacles that limit the allowable takeoff weight. The turn procedure is computed taking into account the climb speed and bank angle used following the engine failure. The effect on climb performance resulting from the bank angle flown during the turns is included in the allowable takeoff weight limit. Because a turn is involved, the obstacle accountability area expands in width to 3,000 feet either side of the track. The procedure may be defined in simple terms of turns and headings to fly following an engine failure. Ground-based nav aids are usually used to identify the point at which a turn is to begin. Oftentimes, it is beneficial for the engine failure procedure to coincide with the IFR departure procedure used for that runway. The engine failure procedure for Aspen's runway 33 is based on the LIN's standard instrument departure. The major difference is that the turn points are expressed as geographical references instead of crossing altitudes. In addition, this procedure includes a holding pattern at LIN's intersection that allows the airplane to climb to a safe altitude and reach the IFR en route structure. Although not used in this example, there is an option to reduce the obstacle accountability area through analysis of the ground track taking into account wind and available course guidance. Another option provided in the AC uses visual guidance to avoid obstacles. While this may sound simple, the AC requires that specific procedures be provided to the flight crew along with any weather or lighting requirement necessary to maintain reference with the desired ground track. IFR procedures like the LIN's standard instrument departure often contain minimum climb requirements. As mentioned by our flight crew in the Aspen briefing, this SID has a climb gradient requirement of 465 feet per nautical mile, up to 10,000 feet MSL. Over the years, pilots have asked many questions concerning the climb gradients published on SIDs and obstacle departure procedures. They have heard a variety of answers, some of them quite dubious. Let's answer the most important question first. All IFR departure procedures are based on normal airplane operation and assume that all engines are operating. Compliance with the climb gradient published on a SID or ODP is based on the normal all engines operating climb performance of the airplane. There is no requirement to demonstrate compliance with a SID or ODP based on one engine in operative performance. If an engine fails on takeoff in a transport category airplane, the operating rules and procedures previously discussed are used to address that failure. The IFR departure procedure is no longer applicable. The pilot should refer to the engine failure contingency procedure for the runway in question. This procedure was developed to address this specific failure. The climb gradient published on a SID or ODP is treated as a plane, originating at the end of the runway, that must not be penetrated from above until reaching the published altitude, as opposed to a gradient, which must be exceeded at all points in the path. The climb gradient will provide obstacle clearance based on the assumption of normal all engines operating performance. However, the climb gradient on a SID may also be established to meet an ATC requirement, such as separation from other airplanes, and therefore may be greater than what is required for obstacle clearance. These climb requirements are determined in consideration of all aircraft that are authorized to use the procedures and the full range of airspeeds that may be flown by departing aircraft. For example, 250 knots below 10,000 feet. On the other hand, the contingencies procedure for an engine failure on takeoff are developed based on the demonstrated performance for a specific airplane type. The airplane's flight track can be accurately predicted based on the actual speed flown following an engine failure, for example V2 speed. Therefore, as we have seen, the area in which the obstacles that must be assessed for net takeoff flight path clearance is smaller than the area used for normal IFR departures. The flight management systems on many business airplanes provide features for computing airplane performance, including climb weight limitations. Pilots should be aware that the results provided by these systems are only as accurate as the obstacle information entered by the pilot. If the pilot enters the climb gradient requirement published on an IFR departure procedure, the results may be misleading. Hutchinson, Kansas runway 13 has a very simple obstacle departure procedure. Climb heading 132, which is the runway heading to 3,100 feet, MSL, before proceeding east. Since no climb gradient is published for this runway, the standard 200 foot per nautical mile requirement is assumed. The FMS for this particular aircraft is capable of computing the maximum allowable takeoff weight based on a climb gradient requirement. The climb gradient we use to determine our maximum allowable weight is the 200 feet per nautical mile standard climb gradient for runway 13 at Hutchinson. We determine our maximum allowable takeoff weight using a typical summer temperature for Kansas, 40 degrees Celsius, which is equal to 104 degrees Fahrenheit. Maximum allowable takeoff weight computed by the FMS for runway 13 is 38,336 pounds. The takeoff field length required is 6,889 feet. Runway 13 is 7,000 feet in length. The declared distances for runway 13 are all 7,004 feet, which is slightly longer than what is shown in the FMS. 38,047 pounds is slightly below the takeoff weight limit. The results returned by the FMS appear to show that we are within approved limits for takeoff on Hutchinson's runway 13. A check of an airport analysis for this runway at 40 degrees Celsius reveals a shocking surprise. The takeoff weight is obstacle limited on this runway to 36,841 pounds, almost 1,500 pounds less than the weight shown by the FMS computation. The answer to this question is found on the obstacle departure procedure for runway 13. Here you will see a list of obstacle notes. These obstacles are tall enough that they would normally require a higher than standard climb gradient. To avoid publishing needlessly excessive high climb gradients to the height of 200 feet or less above the runway, the FAA publishes notes about these obstacles on IFR departure procedures. These notes are intended to advise the pilot of close-in obstacles so they are aware of them and can take the necessary actions to avoid them on takeoff. While these obstacles may not be a significant factor with all engines operating, when required by the operating rules, the airplane's takeoff weight must ensure that these obstacles are cleared vertically by the prescribed amount should the engine fail during takeoff. Here's what the performance engineer would see when checking the obstacle clearance at the 38,047 pound takeoff weight computed by the FMS. The engineer would see that the net takeoff flight path does not clear the obstacle by the required 35 feet and that a steeper net takeoff flight path is required. Here is how it might look to the pilot. Not only does the net takeoff flight path not clear the obstacle by the required amount, the obstacle is very close, less than 35 feet from the predicted actual one-engine inoperative flight path of the airplane. Hutchinson, Kansas is not an isolated example. A review of the obstacle notes on many IFR departure procedures reveal that the presence of low, close-in obstacles can be a significant limitation on takeoff weight. In addition, there are many other obstacles that are too low to affect the SID or IFR departure procedure standards, but must be considered in the engine out analysis. As we noted earlier, the climb gradient published on an IFR departure procedure is based on normal all engines operating performance. This often leads to a question: how do I know whether my airplane can meet the published climb requirement? This is not a subject addressed by the certification rules. Therefore, all engines operating takeoff climb performance data is not furnished in the FAA-approved airplane flight manual. As we have seen, there is a requirement to furnish one engine and operative climb performance data in the AFM, but using this data to show compliance with a climb requirement published on the IFR departure procedure is not required by any operating regulation. Some manufacturers may provide supplementary all-engine climb performance data, but if that data is not available, pilots should use their knowledge of the airplane's normal performance capabilities to determine whether they can comply with this climb gradient on a particular takeoff. To aid the pilot with this determination, the U.S. Government Terminal Procedures publication contains a chart that converts the required climb gradient into a corresponding rate of climb value that the pilot can reference during the departure. On Jepeson's charts, this information is published on the procedure chart. The question of what action a pilot should consider or take when the engine failure procedure differs from the IFR departure procedure is worth addressing. At terrain-challenging airports like Aspen, the engine failure procedure typically conforms to the IFR departure procedure for the takeoff runway. However, modifications may be necessary to identify the start of any turns using precise geographical references instead of the altitude crossings that are frequently used on SIDs and ODPs. If it is not already available, it may be appropriate for the operator to request an engine failure procedure that does align to the SID or ODP to the extent necessary for the airplane to reach the IFR en route environment. As we saw at Aspen, this may involve the use of a conveniently located holding pattern.
But the AC 120-91 prescribes a flight track of the airplane, and it's got to be clear of obstacles within this containment area for nothing else. That is defined by the edges of the containment area, which are the green and red lines. It looks like they come together here. Actually, as you get further from the runway, the splay, as we call it, widens to about 2,000 feet when you're straight out. And if you have to do a turn, it increases to 3,000 feet in a turn. So we have two ways to clear obstacles. One is called an area analysis method, where you have to take into account the winds and so forth, and get an obstacle analysis of what lays in this area here, and you've got to clear it. And so that's very difficult for a normal pilot to go out and get an obstacle database to do that. That's why you need these professional people to help you do that. And particularly when you get in a turn and it expands to 3,000 feet in a turn. The second part of this is called a track analysis method, which I like a lot better because that's where you can use RNAV and you stay on a defined track. You follow the magenta line, if you will, and you're very, very precise on what you can do in terms of your one-engine inoperative departures. We're looking, for example, at now using required nav performance AR, authorization required, precise RNP AR departures for airplanes that are capable of flying them down to maybe 0.1 to be able to fly OEI tracks. And if we can get to that point with that kind of aircraft technology, we're there, I think. We just have to develop the criteria and the new splays for that. We'll be able to get the minimums on those approaches a lot lower because you've got a missed approach clearance capability that's defined with that new technology.
However, some additional pre-departure planning may be required when the engine failure procedure maintains a straight-out track, or if the engine failure procedure differs significantly from the IFR departure procedure. When taking off from runway 9, the San Diego Lindsay SID turns left to a 275-degree heading after passing 4,000 feet. However, the engine failure procedure for this runway calls for a right turn to a 180-degree heading after passing the ISAN 4.0 DME. In this example, if the engine fails prior to reaching 4,000 feet, the pilot is still able to follow the engine failure procedure. On the other hand, if the engine fails after attaining 4,000 feet and in the left turn, the engine failure procedure is no longer applicable. At this point, though, the airplane is above the immediate surrounding terrain. The pilot has any number of good options available. However, it might be wise to think about these options as part of your pre-departure planning. Here are some strategies you may consider applying when the IFR departure differs from the engine failure procedure, or when you expect ATC to provide vectors after takeoff. First, climb as rapidly as practical to 1,500 feet above the airport elevation. Doing so with all engines operating gains altitude quickly close to the airport, mitigating the effects of an engine failure later in the departure. If the engine fails on takeoff at V1, fly the engine failure procedure. If the engine fails during the initial climb out, fly the engine failure procedure if you are still closely aligned with its track. If the engine fails at this point, the SID or other instructions assigned by the ATC are no longer applicable. When time permits and the airplane is under control, advise ATC of your intentions. Controllers are trained that the pilot of a transport category airplane will utilize a contingency procedure in the event of an engine failure. If the engine fails after the airplane has turned away from the engine failure procedures track, the option of turning back to rejoin the procedure does not necessarily guarantee obstacle clearance. This is where the altitude gained in the initial all engines operating climb is of greatest benefit and provides additional safety. Turn away from known obstacles. Use the terrain display of the TAWS or EGPWS to identify high terrain or obstacles along the current flight track. Use the peaks mode, if available, to identify the height of these obstacles and to assess the need for a turn. The approach chart will portray prominent obstacles, however, pilots are cautioned that not all obstacles are shown on these charts. Finally, seek assistance from ATC. ATC can vector the airplane away from high terrain or obstacles. If necessary, request vectors or a hold from the controller to reduce crew workload while addressing the emergency. When taking off from an airport with limited ATC services or radar coverage, be familiar with the minimum safe altitudes or terminal arrival area altitudes for the approaches serving the airport, especially in the areas encompassing the takeoff and initial climb out. The MSA or TAA for an RNAV approach is centered on the runway threshold. These altitudes provide at least 1,000 feet of obstruction clearance within a particular sector. Once above these altitudes, a turn back to the airport can be safely accomplished, provided you remain within the maximum distance published for the MSA or TAA.
Okay. Before takeoff checks, please.
Now that we've reviewed considerations for takeoff obstacle avoidance that should be part of every pilot's pre-flight planning, let's see how this planning enters into play when the engine fails on takeoff. We join our flight crew as they receive their takeoff clearance from Aspen's runway 33.
Tower, November 300, Charlie Charlie's ready for takeoff.
November 300, Charlie Charlie. Winds are light and variable. Altimeter 29092. You're clear for takeoff. Runway 33.
Clear for takeoff, runway 33, November 300, Charlie Charlie.
Finals clear.
Clear on the right. Runway heading is 328 and we are cleared for takeoff.
Firm.
Takeoff power set. Airspeeds are live. $80 knots, cross check. V1, rotate. Positive 8.
Gear up.
Had the left engine roll back.
Okay. There's the end of the runway. Coming 340, heading half bank. Speed Buck V2.
Set. Looking for 10.3 miles.
Copy that.
November 300, Charlie Charlie. Contact departure 123.8. Have a good day.
November 300, Charlie Charlie, switching.
And when you get over there, go ahead and declare an emergency.
Departure November 300, Charlie Charlie's with you, declaring an emergency. 5 souls on board, 3.5 hours of fuel. We've had an engine failure. We're flying the Lens departure procedure. We'll be holding at Lens on the 244 with left-hand turns.
Roger, November 300, Charlie Charlie. This is departure. We acknowledge your emergency. Report entering the hold at Lens.
We'll report entering the hold November 300, Charlie Charlie. There's 10.3.
I'm in the turn to 270. All right, we're looking for an acceleration height of 9,330. If you would help me watch for that.
Will do. Passing 9330.
Accelerating 170.
Amps available. Would you like the engine failure checklist?
Engine failure after V1, affirmative.
Engine failure procedure above V1. Rotated VR pitch attitude adjust is required to achieve V2. Landing gear up after a positive rate of climb. Climb at V2 until clear of obstacles, then accelerate to V2 plus 15. Flaps retract. Then climb at en route speed. That's where we are right now. And I have the engine shutdown in-flight procedure.
Go ahead.
Thrust lever.
Confirmed?
Left
Change.
engine run switch off. Confirm?
Confirmed.
Rudder trim as required. Electrical load reduce. Bleed switch off. Cross flow open. Anti-ice off. Monitor fuel balance. Cross flow is required. Transponder goes to TA only. Land as soon as practical. Next is the engine air start procedure or the single engine landing procedure. Your choice.
We'll do the engine air start. There's no reason not to. We'll use the APU assisted one, so we'll get the engine restarted if we can, and we'll proceed get a clearance over to Denver as we discussed previously, and just soon not go back into Aspen.
Concur.
We will probably need to climb to at least 17 or 17,000 or flight level 190. We can ask ATC, but that shouldn't be a problem.
Roger.
And if you want to tell him we're crossing Lens, entering the hold.
Approach November 300 Charlie Charlie's entering the hold. We're going to run a checklist and then proceed to Denver. We'll advise when we're ready.
Roger, 300, Charlie Charlie. We mark your time entering the hold. Let us know how you wish to proceed.
As we bring the discussion to a close, it is beneficial to review a few key points. Part 121 and Part 135 operators of transport category airplanes have a legal requirement to ensure that the net takeoff flight path clears obstacles following an engine failure at or above V1 speed. These operators must consider takeoff obstacle clearance for every takeoff. It does not matter if the airplane is operated under instrument flight rules or visual flight rules, or if the weather conditions are VMC or IMC. Though not required, voluntary compliance is strongly encouraged by Part 91 operators. The climb gradient requirement, published in a standard instrument departure or an obstacle departure procedure, assumes normal all engines operating performance. Demonstrating that the airplane can meet these climb requirements after an engine failure is not required. If the engine fails on takeoff at or above V1 speed, fly the engine failure procedure. The SID or the takeoff climb-out instructions received from ATC are no longer applicable. Advise ATC of your intentions when it is safe to do so. As we have seen in the presentation, the determination that safe takeoff obstacle clearance can be achieved following an engine failure on takeoff is not an easy task. Ask yourself, is this assessment something that I can perform before each takeoff? Do I possess the training, the tools, and the skills to analyze the engine out performance of my airplane? Can I determine where all the critical obstacles are along my takeoff path? Can I calculate a takeoff weight that will clear these? An engine failure is an extremely rare event with today's modern engines. In fact, many pilots will never experience an engine failure during their career. However, a study of accidents and incidents occurring between 1959 and 1996 involving engine thrust problems, including engine failure, found that over 70% of these events occur in the takeoff and climb phase of flight. If you should be one of the unfortunate few who experiences an engine failure on takeoff, will you be prepared? Will your airplane have the necessary performance to clear the trees, buildings, cell towers, and the terrain beyond the end of the runway? Performance planning is key if a pilot is to meet these challenges.
Okay, so in the last couple hours, we've presented the whole concept of declared distances, wet runway takeoff performance, landing distance assessments, and departure planning, including all that one engine inoperative. I mean, just a ton of stuff. But I'd like to ask you, if you look back in your own personal experience, when you've had performance planning training in the past, what did you do compared to this? I hope you agree that having the visuals here and having some of the exact examples with particular airports is quite a useful exercise. I think it is. And to get rid of those spaghetti charts is a great exercise as far as I'm concerned. So I'd like to introduce Rogers Hemphill. Are you in the back? Rogers is one of the folks that helped us a lot in the development of this, and he is the he's with APG, Aircraft Performance Group, and I know several of you probably use APG. And like Gary with ASAP, we really encourage, the FAA really encourages that the Part 91 guys particularly take advantage of these services, because it's just too darn complicated. I think you can agree with out there. If you need anything on this information, that's my name. Bruce McGray couldn't make it. He's trying to keep an 80-foot oak from falling on his house in Maryland right now, so he's out with a bunch of chains in the wind. And Chris is here, and we are the three respondents to this presentation for anything you need from us. Like I said, in a couple months, we're going to have this available to all you folks out there to use as you like in your own particular training programs. We're going to have available online. It's the first time we've ever done this in the FAA. Actually tried to give something to the industry instead of taking it away. And so we hope you like it. And appreciate your attention. And do we have any questions here before we close it out? Yes, sir.
One more, I'm sorry.
That's fine. No, that's why we have these folks here.
You know, there's a defined moment where you have an engine failure. It's an easy, no-brainer situation. In most cases, if it happens at B1 all the way up to 400 feet. But the most challenging part for crews, I think, and pilots alike, is that what happens when that engine failure occurs when you pass the point of the engine out maneuver. Let's say, for example, it happens at 1,500 feet. It goes completely in the opposite direction.
Right.
And you have that engine failure.
Right.
You're using visual maneuver to maintain obstacle clearance. You're using ATC, or you continue along the standard issues departure procedure.
Yeah.
Mentally, people have a hard time adjusting to the fact that they don't know what the climb gradient performance is going to be if they continue along the SID to assure that they're going to maintain and clear that obstacle that they've been given on the SID. They just have a hard problem. I know that what Terp says is that, you know, the technical term is that you cannot penetrate the plane from above during the departure procedure. So the big question is, how am I assured once I'm past that point that I'm going to meet that climb gradient so that I don't penetrate that plane from above during an engine out after I've already passed that point and I continue along the SID?
Yeah, you're in no man's land. It's what you're feeling, right?
Right.
Anybody want to? Yeah, because that's a great question. And does everybody understand the question? You're in no man's land after 1,500 feet. So,
Well, actually, that's part of the engine out analysis. It's in the olden days, we might have just did an assumption you're going to do a straight out departure after an engine failure, and we didn't look beyond what we call the OC chart, beyond a couple miles or so. But all that's changed as we've gotten into more difficult airports, and we realized that that's just not good enough in mountainous terrain. And then we realized after we analyzed those airports, the difficult airports in mountainous terrains, hey, there were some flatland airports there. New York might not have mountains, but it has buildings too. So we've enhanced our procedures, and I think most of the providers, and I'll let them speak to it, I think most of the providers have enhanced their analysis, so they do carry it out. And fortunately, once you get beyond a point at which the two paths diverge, usually it's pretty simple, and it's a pretty almost a slam dunk that you can fly the SID unless it takes you over extremely high terrain or climbing out of a big valley or something like that. And quite frankly, it was no coincidence that the minimum climb gradients assumed in the TERPs are not that different from the engine out climb gradients required for certification of Part 25 and Part 23 airplanes.
Okay.
I just want to add a little bit to that. As a goal, when we're looking at the prospect of engine failure, we're going to keep the all engine and engine out procedures along the same track as much as possible, and ideally we'll give you an altitude above which you're assured that you can complete the all engine procedure with an engine failure. It's not always possible, but when it is, that's the way we want to do it.
Yeah, I also like the first idea of saying, okay, now that we know what we have in GPS and RNAV and all these great machines that give us a spot-on performance as far as navigation goes, why not just build them nowadays to meet the requirements of the lowest terrain during departure? Then it would be a no-brainer.
Yeah.
I'd like to second that, Rob. All of our departure procedures, our goal is to keep them together until you can safely fly the SID if you lose an engine past that point. I can only think of a couple that we've had over the years where we might have two decision points, where an early engine failure would require quick return, stay within the confines of the airport in the immediate valley, and then a second would be, okay, you get farther out and then you have an engine failure. You can't continue on over the ridge line, but you've got to do a different return.
Anybody else? Okay. Yes, sir.
The question I have, we use APG, and some of the departure procedures vary from the standard SID. So the question I always have is, how do you transition in an engine failure scenario from the SID to the other procedure?
Well, it depends where she quits. And like the
Providers are never really able to answer that question. So what we do is only use those that mirror the SID, so we don't have a decision.
yeah, whenever you can, that's obviously the best solution. But there are going to be, we can all come up with scenarios where you're in no man's land. I mean, it's just a fact of life. So we reduce that as much as we can. But that's why I like, that.
I steer our people away from no man's land as much as possible.
Yep.
But if they are there, what's the regulatory issue with navigating without being on a particular departure, in between the two departure procedures? Or is there?
No, there frankly isn't.
The regulation is the pilot's responsible for terrain clearance.
Yeah. You declare an emergency and you can do whatever you want. I mean, it's very difficult. But I think we've narrowed down, the options. That's why I love that Reno thing where the missed approach and the one engine is the same thing. Whenever we can do that, we try to do that, And as the technology improves with the airplanes and we get this containment down and down, we're going to be able to do that, I'm quite sure. So, sure.
Correct me if I'm wrong, I believe that one of the goals, one of the missions of this initiative is to standardize the training of aircraft performance.
That's correct.
Is there, I can't remember when you guys were working on this, is there a specific set of milestones when you're going to roll that?
Yeah, we have about 2 years of goals and milestones established. One is, we own the 142 schools certificates, so we have folks in the 142 program that we've already talked to about starting to standardize the performance instruction in these schools. We know we need to do a lot better for our POIs. I know we have general aviation POIs out there who are overseeing jet operators who don't have a type rating. That's egregious. But that's facts of life. But we've got to do something to spool those people up. what is a 135 aircraft performance program? Is it part of the General Operations Manual? Is it something that's approved or accepted by the FAA? Those are all questions being asked all the time, and it's not clear at all in the regulations, 135.21 or 23 or any of them. I believe it's something that's accepted as part of the GOM, so we can keep, you know, the hard litigation out of it. But Rogers.
Rick, your question has 2 points to it. You know, one is from the FAA standpoint, which obviously Kobe has addressed. The other is the training providers themselves can take the initiative. Right now, I'm not here to advertise for anybody, but one of them is in the process of generating a standardized program as a corporate policy. Then they will leave the individual aircraft, because now you get into one aircraft has this type FMS, a later series has a different FMS. Some are dual, some are single. So they're leaving the individual centers. We'll each assign a person that's responsible for an aircraft type and design the best way to implement, you know, engine out procedures in that series of model aircraft. So, you know, there's the regulatory side that's going to, you know, tell the schools what they need to do, but also at the grassroots level, there is action occurring right now at the training centers themselves. That's in the
Yeah, that's a great point, Rogers, to bring up. Yeah, because, you know, what we can bring you as the regulators is this stuff. You know, 35 feet that came in June of 1941, before Pearl Harbor, and it's still there. I mean, 115%. Well, it's 10 isn't enough. 20 is too much. So let's go with 1935. So those regulations, the A380 was certificated with V2 at 35 feet because it works. So there are ancient regulations there. There's regulations we're missing. I know that for a fact. But I don't want to get into rule-making business. I'd rather get in the outreach and the standardization and training and the understanding business for our pilots out there to be able to understand this stuff. I mean, it's just a tremendous lot of material here. And, you know, I'll leave it up to you folks on what you do with it. Anybody have anything else? Okay, well, I appreciate, I'm sorry, sir. We got one more.
Yeah, I like the point that you said about how the technology is advancing, the NBAA stuff.
Yeah.
And industries, I think, doing their part. And we could get FAA on board too in terms of making sure that LOAs get done quickly. So that
Yeah.
Because they advantage of those technologies. We know that's a major deterrent right now. There's such a huge backlog of LOAs.
Yeah, I mean, it just 8 years ago, they were slapping gizmos on airplanes to make them RNP .3 airplanes. Now the airplanes are built as RNP .1 airplanes integrally into the system. So it comes out with RNP .1 on the box, you know. And so we've got to adapt very quickly, I think, to accommodate that kind of technology. And I want to do that because I think that's really important. We do that, recognize that you go out and spend the money for these airplanes, we've got to give you the maximum amount of capability that you can participate and operate with them to do. I'm the U.S. member to the ICAO Ops Panel. We just formed a subgroup up there called the PBN Performance-Based Nav Subgroup, and its first order of business is to talk about OEI, RNPAR departure procedures. So, yeah, that's an international interest for great reasons. So, anybody else?
Yeah, in the future, I think the vision I see is you have the departure loaded into the FMS, you get an OEI situation, and then, you know, you have line select key where you could just fly automatically the RNPAR.
Absolutely. Absolutely. It's got to be a no-brainer. You know, that simulator session when you're sitting here, or especially if you're a sim instructor, it just seems like it went on and on forever and ever. You guys know if you're in those seats, it goes that fast. You know it's like, right? I mean, it's a lot different when you're sitting in the seats and everything, and you're at Aspen, and holy cow, what are we doing in this place? So I'm going to shut it down now. I'd like to thank you very much for your attendance. Wish you a Moria. Thanks, and keep apprised because the TAP's not going away. There's a lot more coming from it in the next couple of years. We're going to keep these guys busy. Thank you very much, folks.